Okay, we are back. And we've got, let me make sure I've got all the ducks in a row here. Zoom screen. That's good. There. That is perfect. Okay. Hey, guys, thanks for joining back again. This will be part 4, which should be the final part for the general class upgrade live stream on this channel, taught and put on by the North Richland Hills Amateur Radio Club in North Texas. You can find their website at nrharc.org. They are, I forget their call sign right now. It's K5 NRH or something like that. They were gracious enough to allow me to live stream this event. So this is a Zoom session for a Zoom link that they sent out to a bunch of people and allowed people to join. And they're going through the W5YI material for the purpose of license upgrade for anybody who's a technician who's got a current license that wants to upgrade. There were 2 parts done last Saturday, parts 1 and 2, both before and after lunch. Part 3 we just finished about a half hour ago. All of those are replayable on this channel, and will remain so for a long, long time. And I'll probably take those episodes and chop them up a little bit, cut out all the live stream info, the intros, the exits, and the transitions in the middle and stuff like that, and just get the meat and the guts of the material being taught and put them up in another series of videos on this channel, maybe in the same playlist that these are in. The Hearst Amateur Radio Club, who I have done several classes for in the past, did a live general class last November before all the lockdowns happened and everything. I recorded and posted that last November on this channel. So this material has already been covered. Okay, but it's good to have different perspective, different teachers, different ways that different explanations of different questions and everything. So now you've got a choice. You can go back and watch the Hearst class, which is 9 parts. I split those up into 9 different parts. So you can, that was not live streamed. That was recorded and edited and posted later. And now you can watch the live streams of the North Richland Hills class, parts 1, 2, 3, and 4. And then later, once I chop this up and put it in the smaller category or smaller episodes, you'll be able to watch those too. So you'll have 3 different choices of classes to watch for general class upgrade if you are a technician and wanting to get an upgrade. Or if you're new to ham radio, you don't have a license at all yet, and you want to take your tech and your general class at the same time, you can do that. I know folks who've done that. I know one guy in the Hearst Club took all 3 of his tests at the same time. So it's certainly doable. But anyway, thank you for being here. Those of you who are here, see John in the chat. And we're about to get started here. It looks like these guys are back. Let's see. There's that. And we'll switch over there, and we're going to go ahead and unmute their audio.
And Jeff was helping me put the stuff up on the screen. There was some kind of an issue, but we finally got it straightened out. And he gave me the permission for host, so that's good. And that's nice to know. When we were shown, I forgot who showed us how to switch hosts up in the upper right corner.
Well, it was Jason today. I'm glad I'm the last one because I'd really muddle through that.
There's a lot to cover. I to take a general class test, you imagine what it's like taking an extra now. You must have a lot more in it.
Oh, yeah. And the level of sophistication is, I think, significantly more. So, yeah, it would be tough.
Yeah, when I took my extra class many years ago, they didn't have multiple choices. They had some, but you actually had to figure stuff out and
let us know how the audio is on the YouTube channel, guys.
You had to use the
if you don't mind, just put something in the chat. Let us know if the audio sounds good.
It was a little bit different.
Yep.
And of course, I had to pass 20 words a minute code test too.
Oh, yes. Lots of changes since then.
There sure has. There sure has. Well, anyways, I'm just going to be in the background. I'll
Okay.
mute my stuff, but I'll watch so I can learn something too.
Well, if you have any questions, you know, just unmute and feel free to dive right in.
Sure. Be happy to. I had a real good presentation of what the passband filter was and how it works. It's very rare that you can demonstrate how a passband filter works until you get two stations close together where one's really interfering with the other, and then how you can use the passband filter to take out the other station. It took a while. Today they're having a contest, you know, in California. I guess it's a QSO party contest or whatever.
Right.
And people working right on top of one another within 2 kilohertz.
Oh my.
Yeah. And you can hear them loud and clear. And the only way to get rid of it and hear the station properly is to use the passband filters. On these radios today, they work real good. I must admit.
Yeah, the radio. Well, your 7300 is really a nice radio. So it software-defined radios sure have changed the landscape.
You know, here.
I got a quick question.
Yeah.
So the question I had, actually, I meant to do this when Tom was showing, when you can take the separation down to like 1 kilohertz, is that functionally usable? I guess you were saying you saw people within 3 kilohertz. So getting it down at that minute level, can you use the frequency, and can people actually use that in real time or real life examples?
I tell you, yeah, where it may make in single sideband, you wouldn't be able to notice 1 kilohertz difference, but in digital modes using FT8 and some of the others, it may make a difference because there your bandwidth is very narrow.
Okay, thanks very much. I know we're behind. I do want to slow you down, but I appreciate that.
Yeah.
And also could be in CW as well.
Let's see. Do we have everybody back?
I'm back.
Yeah, I'm back.
This is Jamie.
All right, Jamie. Great. Well, let's go ahead and get started. My name is Tim Tango India Mike. I'm up here in the Keller area, and my call is Kilo 5 Tango Golf Sierra. So we've got the last part of your general class license review today. So hope it goes well. It seems like you guys have this worked out, so I'll let you handle your mute any way you want, but feel free to dive in and ask any questions as we go through. And let me know if I'm going too fast or too slow, and we'll get going here. So any questions or comments before I start? All right. So we are on element 3, and we're going to look at circuits. This section's a little tedious. A fair amount of memorization, but I don't think it's too difficult. Just some things to keep in mind, and I'll try and give hints where I can. So if you have a piece of paper there, you might want to just take some notes. So we've got quite a schematic here with a lot of different symbols. So first is what we call an FET, or field effect transistor. It's generally a 3-leg device. Difference between symbol 1 and 2. 2 is a regular bipolar transistor. Figure 1 is the field effect. And if you notice, those lines coming out to the right are straight, horizontal, where in figure 2, the bipolar regular transistor, they have about a 45-degree angle. So just memorize that. That's a field effect transistor. And there is the symbol on the left. All right, now there are a couple of diodes in this circuit. The diode that has two 45-degree lines coming off the end of the cathode is a Zener diode. So number 5, you notice those two slanted lines. That's the indication that it's a Zener diode. And there's the symbol. Very close to a regular diode, but those two angled lines make the difference. All right, NPN transistor. The way you might remember, there's an NPN and a PNP transistor. If you look at number 2, you see the arrow pointing out. The way to remember that's an NPN and not a PNP is you can think of that as not pointing in. That arrow is not pointing in, so it's an NP for not pointing an N. That's just a little memory tool. It's not really what NPN stands for. And there's a closer symbol of it. All right, multiple winding transformer, very popular in a lot of different areas of amateur radio. Multiple windings, meaning if you look at the left and right, we have windings on both sides. So the symbol that just came up on the left is the primary, and the one just on the right with just 2 coils is the secondary. But because it has more than one winding, it's called multiple. So now we have an inductor. I'm sure you covered inductors in earlier sections. The reason it's tapped is we have a third connection coming into it. And if you look at figure 7, that connection comes in toward the bottom. So it's called a tapped inductor. All right, now we get into some concepts here of circuits. Remember, the theory says that resistors in parallel divide. So if we have 3 100-ohm resistors in parallel, because they're equal value, you can divide, well, let's look at the equation first. R is equal to the resistor value, in this case 100 ohms, divided by the number of resistors, which is 3. And this equation is only good if all the resistors are the same value. So 100 over 3, or 33.33 ohms. The long equation is on the right-hand side. So if they were not equal, you're kind of restricted to that equation, which is the reciprocal form, which if you have a calculator, it sure helps with that inverse key. And again, theory part, the total current entering a parallel circuit equals the sum of the currents through each branch. So total current is equal to I1 plus I2 plus I3, or in the circuit, they're using I sub A, I sub B, and I sub C. So the branch currents there, adding those up is total current. No current is coming in from anywhere else, and it's not going anywhere except back to the battery. All right, 3 equal value resistors. Remember, we can use that special equation. In series means that each resistor was 150 ohms. So here we're talking about series resistance. So in the figure, we've got R1, 2 going out to Rn, but in this case, we'll just talk about 3. So if we have 3 equal resistors in series, 400 ohms total mean that each resistor was 150, because you have to have 150 added together 3 times. So resistance in series is additive on the top of that box. And then down below is the resistance in parallel, which we first looked at. All right, so now this is from the questions, so it's good to remember this. It will help you with not having a calculator, maybe. So 5.9 ohms is the total resistance of a 10, 20, and 50 ohm resistor in parallel. The important part to remember here is you have 3 resistors in parallel. Resistors in parallel, the total resistance is always less than the smallest resistance. So we've got a 10, 20, and 50. We know the total resistance has to be less than 10. If they were all 10 ohms, it would be 3.33. Well, we've got a 20 and a 50 ohms, so that's going to bring it up a little bit higher, but we won't get to the 10 ohm because resistance in parallel actually divides. So if you were to work that equation, first line is just the basic equation, and they substitute in the resistor values. The inverse key on your calculator works really great. You can just invert those numbers, save them, and then do an invert at the very end. So the total resistance is the reciprocal of 0.17, which is 5.88 here. Of course, they've rounded it to 5.9. And here's what I mentioned. Remember, total resistance in a parallel circuit is always less than the smallest resistor. That will help you quite a bit in picking out the correct answer. And a resistor in series should be added to an existing resistor in a circuit. And then the key is to increase circuit resistance. So if a resistor is added in series, it's doing that to increase total resistance. Now we're going to shift here to capacitors for just a short bit. Capacitors kind of behave the opposite of resistors in series and parallel. So the equivalent capacitance of 2 5,000 nanofarad capacitors and 1 750 picofarad capacitor connected in parallel is 10,750 picofarads or 10.75 nanofarads. The key here is when you put capacitors in parallel, those values add. Remember with resistors, when you put resistors in parallel, total resistance goes lower than any of the branches. So capacitors in parallel simply add, therefore total capacitance, and they break it down here and show you 2 5,000 picofarads and then 1 750 picofarad. And they expressed 10,750 picofarads, which is kind of an odd number. So it's probably easier to deal with at 10.75 nanofarads. Pardon me. So here's the circuit and the equation. Capacitors in parallel increase in value. And the reason that is we're increasing the plate space or the total capacitance. So looking into the circuit, they see the plate space or area of each plate or each of the capacitors increasing that value. And the capacitance of 3 100 microfarad capacitors connected in series is 33.3. So you probably see that's opposite than resistors. So here, when we put capacitors in series, we actually decrease the value. And that's because we're increasing the dielectric distance between the plates. So it's 100 divided by 3, or in this case, 33.3. And that's because they're equal value. If they were not equal value, you would have to handle these like resistors in parallel. So C is equal to capacitance value divided by the number of capacitors. And that's true only if each capacitor is the same value. So in this example, it's 100 divided by 3, or 33 1/3 microfarads. And there's the equation for that. All right, the capacitance of a 20 microfarad capacitor.
Can I ask you a quick question?
You sure can.
So does the same rule apply where if you've got different different sizes of capacitors, that if they're in series, then it's smaller than the smallest capacitor, just like?
Yeah. Yep.
Same deal. Okay, thanks.
And that's a good point too. I don't remember the questions offhand, but if you see that in the question, that's a good way to eliminate a number of the possible answers. So good questions, or question. All right, so we have a capacitance of 20 microfarad in series with a 50 microfarad capacitor. Let's see, let me reread that. The capacitance of a 20 microfarad capacitor in series with a 50 microfarad is 14.3. So that kind of answers your question right there. Notice the total capacitance is less than the smallest one. If those two were equal, if it were 250, it would be 25. If it were 220, it would be 10. But we've got 120 and 150. So you know it's going to be a bit above 10 microfarads. But to do it with the equation, you would have the reciprocal of 1/20 plus 1/50. Take the reciprocal of each, add those together, take the reciprocal overall, and you get the 14.285. And the equation is there on the right. And it helps in the test. That equation is essentially the equation for resistors in parallel. So if you can remember it, the one for series parallel, just reverse it for resistors and capacitors. So a value of a 22,000 picofarad capacitor in nanofarads. So what they're doing here, I guess this is a question. They're moving the decimal point from pico to nanofarad, which moves it 3 places to the left. So in 22,000, the decimal point is just to the right of the last 0. But if we want it in nano, we need to run that back to the left 3 places, so we get 22 nanofarads. The reason this is kind of interesting is sometimes you deal with some capacitors that are given in nanofarads, and in the same circuit, another one might be picofarad, but you want them to be in the same value, or the same unit of measure, so you can use that equation above correctly. So the value in microfarads, which is MF of a 4,700 nanofarad, is 4.7 microfarad. Again, we move it 3 places to the left, which gives us our decimal of 4.7 microfarads. And I generally see capacitance values in microfarads more often than nanofarads. And kind of a key question: to increase the capacitance in a circuit, a capacitor in parallel should be added. So this goes back a couple slides ago where they talked about adding a resistance in the circuit increases the value. If we want to increase the capacitance in a circuit, you want to put another capacitor in parallel because it increases the plate space, which is how one of the attributes of how capacitance is determined. Now we jump on the same slide to inductance. Now let me make a quick note about inductance. When we talk about total inductance in a circuit, those equations are like the resistors. So if you add inductance, it increases the value, add them in series. If you put inductors in parallel, it reduces the value. So if you want to increase the inductance in a circuit, you have to add an inductor in series. All right, so now on to inductors. The inductance of a 3 millihenry, the inductance of 3 10 millihenry inductors connected in parallel is 3 1/3, just like resistors. So you want to take and divide the total the inductance. In this example, it's 10 millihenry. That would be in the numerator. In the denominator, you would have 3 because you have 3 connected in parallel. So you have 10 over 3, which is 3 1/3 millihenry. So inductors and resistors behave or use the similar equation. Capacitance uses the opposite. And there's a little or an example of inductors in a circuit. Actually, 3 of them there, you can see. All right, the inductance of a 20 millihenry inductor in series with a 50 millihenry inductor is 70. So if you remember, they add together. So you've got 20 plus 50, which is 70, just like a resistor. And notice they're both in the same unit. It's not like we have 20 millihenry and a 50 nanohenry. That would be a little different. We'd have to convert them to the same unit to measure there. But here they're the same, so it's 70. Okay, now in the training you've had, maybe even beyond this course, resistance we generally refer to as the opposition to DC current. Reactance is defined as the opposition to the flow of alternating or AC current caused by capacitance or inductance. So resistance we use when we have a pure DC circuit or we're talking about DC. Reactance is a component that opposes current flow by an inductor or a capacitor in any circuit. Let's see, all real world inductors have a certain amount of parasitic capacitance. That's capacitance. If you remember the picture we just saw, you had those coiled windings that were the inductors. Well, there's actually capacitance between those windings. If you think about it, if you take 2 windings, you have 2 metal plates or wires separated by air. So that's what we refer to as a parasitic capacitance. And as frequency goes up that's being applied to the circuit, capacitive reactance is reciprocal. So the circuit becomes more capacitive. So if you have inductors in a circuit, there is parasitic capacitance, especially at the higher frequencies. And when that happens, the circuit becomes more capacitive. Not as much inductive, but more capacitive. These are the 2 fundamental equations. So an inductor opposes current flow, and its equation is X of L is equal to 2 times pi, use 3.14, times the frequency in the circuit times the inductance. That's what the L is. I don't know if you can see my pointer or not, probably not, but the L is for inductance. And if you note, well, let me go over to capacitive reactance. Both of these reactances, remember, is opposition to AC current flow. What we note though, and it's tied directly to that second item above, is we have the reciprocal of 2 times pi times frequency times C, or capacitance. So for capacitive reactance, as the frequency goes up, opposition goes down. It's the inverse relationship here. Inductive capacitance, if we have an inductor in a circuit and the applied signal goes up in frequency, so does the opposition, the X of L. There is a unique situation in radio circuits where when we have X of L equaling X of C, we call that the resonant frequency. You've probably heard that term maybe with antennas. you want a resonant frequency for your antenna. Well, that's when X of L equals X of C. And just as a side note, they both cancel each other out. All right, those are the same equations again. Remember, resonance does occur in a circuit when X of L is equal to X of C. We're talking about two different components here. X of L involves the inductor. X of C is the opposition provided by the capacitance in the circuit. And when X of L equals X of C, this is what we have. 2 times pi times FL is equal to the reciprocal of that same, 2 times pi times FC. All right, so what we do to the left side of an equation, we must do to the right side if we want to keep them equal. And what we do to the numerator, we must do to the denominator in order to maintain equality between the left and right side of the equal sign. So if we multiply both sides through by f, we'll get f squared is equal to 1 over the product of 2 pi L and then 2 pi C. And then if we reduce that equation, what we end up with is frequency squared on the left is equal to the reciprocal of 2 pi squared. That's because if just above there, we've got 2 pi twice, so we square that term. We pull out the LC and we've got that is the second product in the numerator. Or I'm sorry, the denominator. So from the previous page, we have f squared is equal to 1 over 2 pi squared, which is 6.28 squared times whatever L value and whatever C value we have. And if we take the square root of both sides, what we get, or what we have left on the left is the product of 1 over 2 pi. So we take the square root of 2 pi squared, we get 2 pi, but we have to take the square root of LC. So what they're saying here is the resonant frequency is equal to 1 over 2 pi times the square root LC. That's the resonant frequency formula. And I think this is looking worse than your questions are related to this material. He really has, he really dove into this and is going through it. But that's your main resonant frequency equation. All right, remember reactance causes opposition to the flow of alternating current in an inductor. Now that's an important part. An inductor opposes changes in current flow. Remember the ohm from before, 10 ohm resistor. We still use that unit of measure, ohm, for reactance. So reactance causes opposition to the flow of AC current in a capacitor. And as the frequency of the applied AC increases, the reactance of a capacitor decreases. And you'd have to go back and look at that X of C formula. So you may want to make a note of that and take a look at it. Now, as the frequency of the applied AC increases to a circuit, the reactance of the inductor increases. And if you remember that formula, X of L is equal to 2 pi FL. So if any term in that equation goes up, reactance goes up. In the bullet right above, X of C, it was the reciprocal of 2 pi FC. So when that goes up, because it's the reciprocal of, then the reactance goes down. in a capacitive circuit. Now, we've got another term for opposition to current flow. So we have resistance, we have reactance, and reactance pertains to the opposition of current flow in an AC circuit, whether it's inductive or capacitive. Regular resistance is just the ohm you learned about earlier from a pure resistive circuit. Impedance is the third one. Impedance is the total opposition to the flow of current in an AC circuit. So in an AC circuit, you could have resistance, you could have inductance, and you could have capacitance. Well, impedance takes into account all of that. So one method of impedance matching between two AC circuits is to insert an LC, meaning an inductor capacitive network, between the two circuits. That's when we want to match impedances to two different places. We put in what we call an inductive capacitive or LC network. And here's an example of a series and a parallel LC network. First one is an inductor and capacitor in series. Second one, of course, is an inductor and a capacitor in parallel. The reason this concept is important, especially in amateur radio, is impedance matching is important so that you deliver the maximum power to the load. So think of this as your radio transmitter has to send energy to your antenna. If you can match the impedance of your radio to the impedance of your antenna, you will get maximum power to that antenna. If you don't, the power the transmitter is trying to put out, the total power, will not all of that will reach the antenna, so you have less power being transmitted. Devices that can be used for impedance matching at radio frequencies are a transformer. There's a picture of one of 100 different kinds. What we call a pi network. And the reason they call that pi is it kind of looks like the pi symbol. It has a right and a left arm to it and then an inductor across the top. Or actually a length of transmission lines. Sometimes we call that a stub, but those can be used to match impedance at radio frequencies. So 3 different options there. They all do the same thing. They do it a little bit differently, but the end result is the same, impedance matching. All right, when the impedance of an electrical load is equal to the internal impedance of the power source, the source can deliver maximum power to the load. So if you look at their example on the right, they've got a power source, which is that sine wave in a circle. Then they have 1,000 ohm resistor. And then R2 off to the right, which is 10 ohms, we'll assume is the load. So you've got 1,000 ohms on the left, 10 ohms on the right. Those don't match at all. That's a terrible mismatch. But the transformer with turns N1 and N2 will transform that impedance so that power source and 1,000 ohms thinks it's seeing a matched load, even though it's 10 ohms on the other side. And what that means now is that source will deliver maximum power. And again, that source we're looking at could be your radio. And then on the right side, the R2 would be your antenna. Now, those aren't values we associate with radio transmitters, but it's that idea. You want to take power from the source to the output load so you get maximum power transfer. Now, here's another network. The impedance of a low-pass filter should be about the same as the impedance of the transmission line in which it's inserted. So here we have a T-section network. It is a low-pass filter because of the capacitance in the center. So it passes low filters right across those inductors on the top, from the radio source to the antenna load. And when we put a low-pass filter in, it's the same impedance of the transmission line, then again, it's this concept of we get maximum power transfer, which is always what we're after. If we have a 100-watt transmitter, we want to put as much of that 100 watts over to the antenna as we can. Now, another concept of circuits they have is filters. And here we have the cutoff frequency is a low pass filter's output power that is less than half the input power. So the circuit on the right is how we would graph the Bode plot for a circuit that's a low pass filter. So if you notice, we have power out across the top at value 1, whatever that 1 may be, might be 100%. But low pass means it passes the frequencies to the left of where you see 3 dB. So it's passing the low frequencies, but as you go higher, the output begins to fall off. Are you able to see my pointer at all?
Yep, I can see it.
Okay, so you see this almost an S curve. That's where the output of the filter starts dropping off because the filter characteristics say, hey, the frequency's getting too high. We don't want anything higher than that being sent out, say, to the antenna. Well, we define the cutoff frequency as being the 3 dB point, which they define here as the top line and then go down half. Remember, 3 dB relates to half or or double. So we refer to that as the cutoff frequency. Any frequency above f sub c, which means cutoff, we say really isn't going to be passed. And if it is, it's going to be negligible. So that's the cutoff frequency. Because it has this big area here, those are the lower frequencies. It is a low pass filter. And the ultimate rejection specs or specifies a filter's ability to reject signals outside the bandpass. So anything above FC here, we would say is outside the bandpass. And as Tom mentioned this morning, the radios today, like his 7300, they do this with software, and they can get these filters incredibly steep, much steeper than what we see here on the diagram. So the ultimate idea here is we want to reject signals that are not in the pass band. And this is the pass band from 0 up to f sub c is what we call the pass band for this filter. Now here is another filter right below where we have 2 cutoff frequencies. The pass band is in the center, so we want those frequencies in the pass band. Anything below f sub l, anything to the left of f sub l, we don't want. In the fall off here, the roll off of this curve is pretty quick. And then above f sub u, the upper limit, those frequencies or outputs, the output falls pretty quickly as well. So we generally define those as the negative 60 dB point. And again, what we're after in this circuit is we want to pass the frequencies that fall within this range. Now, here's one a little more colorful and a little bit more information. The upper and lower half power points, and we also refer to the half power points as the 3 dB points. So the upper and lower half power points in the frequency determine the bandwidth. So wherever that 3 dB point is where we have half power is what we call the pass band, or in this case, the bandwidth. We've got center frequency here. We've got the high frequency cutoff. And on the left here, we've got the low frequency cutoff, F sub L. So those kind of pinkish areas, if it's in the same color that I'm seeing, those are frequencies we don't want. The bright red in the very center is the pass band. And that's what we want to have. That's what we want to use in our radio and antenna. Now, so that's good. We can get filters, we can put those into antenna lines, and we can cut off frequencies higher or lower. But there's a downside to this a little bit, and it's what we call insertion loss. So insertion loss specifies a filter's attenuation inside its passband. So anytime, especially on the analog side, anytime we put a filter in to get a passband like this, we also attenuate the signal in the passband. Not a lot, but we do lose some of that magnitude for the frequencies that fall anywhere inside this. So insertion loss really specifies a filter's attenuation. And by filter's attenuation, we mean we want the filter to attenuate frequencies we don't want to use, but it will also attenuate some of the frequencies in the passband. And that's just, part of the negative side of using a filter. All right, on the bottom there, we see wire wound resistors. Don't see those too often anymore, but a reason not to use wire wound resistors in an RF circuit, and take a look at those resistors, is because the resistor's inductance could make the circuit perform unpredictable. So those metal things that you see along this resistor, and this is a slider to change the value, they could actually at RF frequencies act like an inductor. And when that happens, we don't know what's going to happen to the circuit performance, but it's not going to be good. So we want to stay away with this type of resistor that's called a wire wound resistor. Now, I think you've studied capacitors in one of the other sections. This is about ceramic capacitors. An advantage of ceramic capacitors compared to other types is they are low cost, cheap to make, very effective, high grade, but cheap to make. So that's the advantage of capacitors that look like this in the photos. Now, these are inductors along the bottom. There are several different types. The advantage of using a ferrite core with a toroidal inductor is we can get very large values of inductance. So if you look at you can see the windings. What those are wound around is the ferrite coil. So you've got examples of those all through here. Well, using that core, we can get very large values of inductance. And the magnetic properties of the core can be optimized for specific ranges of frequencies. So depending on how that core is made, we can get very specific performance out of these inductors. And losses are lower because the magnetic field tends to concentrate in these cores. So your energy is bound up in this core here, still interacting with the inductor, but not going out to other circuits. And that's quite an advantage. So the composition or the mix of materials used determine the performance of a ferrite core at different frequencies. So you use different kinds of materials for different frequencies, depending on what's needed in a given application. The term mutual inductance causes a voltage to appear across the secondary winding of a transformer when an AC voltage source is connected across the primary. So there are examples of that all over. You know, you look down neighborhoods and you'll see transformers from the power company coming in from their source going to homes. Well, they use mutual inductance to step that voltage down, in our case, to go to the homes. So here are three fairly complicated photos. The first one on the left, we have two coils. We have mutually coupled fields here. So the field of one inductor interacts with the windings of L2. Those are short proximity. As you pull those inductors across where there's a larger distance, we don't have as much interaction. Now, when we, in the center, if we look, we have coils insulated but wound around on each other. So we have magnetic field interaction as it shows here on both sides, where you've got that magnetic field coming up through and then going outward from both the primary and the secondary. And as they mentioned earlier, we often use ferrite cores. This is a magnetic transformer core, which is used to couple the primary windings, not directly, but through the magnetic waves that we see in the first photo, to the secondary. So that core captures that magnetic field. You don't see that magnetic field in the third photo on the right, like you do in the center or the first one, because it's captured by that transformer coil, and that's much more efficient. So in order to accommodate the higher current of the primary, the conductor of the primary winding of a many voltage step-up transformer is larger than the conductor of the secondary. So basically, we use transformers to step up voltage, step up or step down voltages. And each time a transformer steps up voltage going from primary to secondary, it does the opposite to the current. So if it steps up the voltage in the secondary by 2, it steps down the current by 50% or half. But that's why you'll find higher current, or I'm sorry, larger wire because of the higher current in the primary of a transformer where it's stepping up voltage in the secondary, but it's stepping current down by the same factor. All right, so transformers, voltage across a 500 turn secondary winding of a transformer is 26.7 volts. If the 2,250 turn primary is connected to 120 volts AC. So what's going on here is they have a transformer, the primary, which is generally drawn on the left, is 2,225. And the output voltage is 26.7 when it's connected to the power source. So there's an equation here that we use with transformers. I'll let that, all right, that drew out. So we have voltage in the secondary over voltage in the primary is also equal to what we call the turns ratio. The number of turns in the secondary over the number of turns in the primary. So those two equations are the same. They will give you, if you have the value of all of those, they'll give you the same result. Now, all right, let's see, it's, well, now it's drawing out. Okay, so if we take the equation, the number of turns in the secondary, which we saw from the problem statement, and we have 2250 turns in the primary, we have that problem where we've got NS over NP for that equation. So if we were to do that with a calculator, we would get 0.222, meaning the secondary voltage or the output voltage of the transformer would be 0.22 times the input. And of course, that would be less than the input. So if we multiply the 0.222 times 120 volts AC coming in, we would get to 26.66 volts, which of course they round to 26.7. So the key equation here, and you might want to write that down or note it in the book, is the ratio of the secondary voltage to primary is also the ratio of the secondary turns over the primary turns. And the output voltage is multiplied by 4 if a signal is applied to the secondary winding of a 4-to-1 voltage step-down transformer instead of the primary. Now this, well, I guess he isn't, the FCC. They kind of threw a wrench in here because we're looking at a transformer through normal application, which the input is on the primary, the output's on the secondary. But here there's a question that relates to if you put a voltage to the secondary of a 4-to-1 voltage step-down transformer. So you're putting the input to the primary of a step down, which is, we normally would think, well, that's kind of backwards. So let's look at an example of the turns ratio of a transformer used to match an audio amplifier having a 600 ohm output impedance to a speaker having 4 ohms. So here's an application where a transformer is really good because we want to match the impedance or the resistance of the source to the load. Well, we've got 600 ohm and we've got 400 ohms. That certainly doesn't match. And it would be a terrible connection if we were to just connect those wires together without any kind of matching device. So if we remember the equation from the last slide, the turns in the primary over the turns, well, NP meaning number of turns in the primary over the turns in the secondary is also directly equal to the impedance of the primary over the impedance of the secondary, and then take the square root of that. So here we happen to know the impedance of the primary and the secondary, 600 and 400 ohms, which is also, by the way, what we refer to as turns ratio is the number of turns relative to primary and secondary to make that equation. So to do that, we have 600 impedance for the primary, that's the output of the amplifier, divided by 4. And then when we do that, we get 150, and then we take the square root of 150, which is 12.2, and that's what is referred to as the turns ratio of the transformer that would be needed. So if you had this circuit connection, you would want to go out and look for a turns ratio of 12.2. So you'd go through the catalogs, or in this case, you might even think about building one. And again, that's a turns ratio problem. All right, so let's see here. We've got some questions now. All right, this goes back to the beginning. What symbol in this figure is the field effect transistor?
C, Charlie.
See,
Yeah.
Charlie.
Yeah, it looks good to me. Remember, they have the horizontal lines. Which symbol in this figure represents a Zener diode? And although we have a number of diodes in here, there's only one. That's
D
a
is in delta.
D,
D.
delta.
All right, very good. All right, which is the NPN, which just is a memory device. Remember, it's not pointing in.
Number 2.
And that
B.
would be
Bravo.
D is in Bravo.
Bravo.
Bravo, number 2. Correct. All right, which symbol in this figure is a multiple winding transformer?
Bravo.
Everybody agree?
Or no, it's Charlie.
Sorry.
Let's say it's C. Charlie.
Charlie.
There you go, Charlie. Yeah. Now, well, I think we'll get to the answer, the other one you guys were thinking of. Yeah, this one. Which one is the tapped inductor?
Yeah, that one's
Yeah.
A7.
alpha.
A.
And just remember, the tapped inductor, at least as far as the test is concerned, will only have 3 connections. Here, here, and here. Whereas the multiple turned, I think they call it, transformer has 2 on the primary and 2 on the secondary.
Good to know.
Yeah, 7. So we got that. All right, total resistance of 3 100 ohm in parallel. Now remember, resistors in parallel divide.
Charlie.
Yeah,
See,
resistors
Charlie.
in parallel divide. So it's 1/3 of 100, which is Charlie. The others all have a 3 in them, but decimal point's not right. All right, how does the total current relate to the individual currents in each branch of a parallel circuit? Any
My
idea?
guess is A.
Yeah, I was guessing that as well.
Now remember, this is parallel.
Parallel, they add. There is the cumulative value. So it's
So what would the answer be?
C as in Charlie.
Yeah, they add together. So currents in a parallel circuit add together. So total is equal to the sum of all the branch currents. Good. All right, 3 equal value resistors in series produce 450 ohms. So what you have to think about here is you have to take one value, add it together 3 times to get the correct answer.
Charlie, of course.
Yep, Charlie.
Yeah. And of course, they make it kind of easy because they say equal value. All right, what is the total resistance of a 10 ohm, 20 ohm, and 50 ohm in parallel? Now remember, the rule of thumb is resistors in parallel, the total resistance is always equal than the smallest branch.
So A, because B is way too small.
Exactly. C and D don't make sense at all, but you're right. B is way too small because those values really aren't too far apart. All right, which of the following components should be added to an existing resistor? So if you put resistors in series, what's the total do?
It adds. So it would be B.
In series, they divide.
No, this is now remember
No,
we're
parallel. Opposite. Sorry.
Yeah.
Oh. Okay, here we're talking about series, right? Oh, here we're saying if we want them to add, yeah, we have to put them in series. Putting them in parallel, they divide. All right, let's jump to the other side of the fence here with capacitors. What is the equivalent capacitance of 2 5 nanofarad capacitors and 1 750 picofarad connected in parallel? So forget about the answers for a second. What happens to capacitors when we put them in parallel?
They add.
Exactly.
And they got sneaky here. They changed the capacitance from our discussion. They changed how they phrased it.
Oh, yeah, that wouldn't surprise me.
So it's D, but they're still trying to be tricky.
Yeah.
Well, what I saw was tricky. They put two capacitors nanofarad value. So you could add those two together. You've got 10. but the picofarad is in different units. So, all right, what is the capacitance of 3 100 microfarad capacitors connected in series? Now, capacitors are backwards from resistors. If we put capacitors in series, what do?
They divide.
Divide. All right, so if we have 3 of equal value,
BC, Charlie.
very good. Yep, they're equal value, so you just divide 3 into 100. What is the capacitance of a 20 microfarad capacitor in series with a 50 microfarad? So again, they're in series.
B,
How come?
because it's got to be, that's dividing, so it's got to be lower than the smallest capacitor. Oh, and 50 micros is, no, 20. It's so 20 microfarad's a smaller one. It's got to be smaller than that.
And just like I think you said before, the 0.07 is way too small.
Way too small.
Exactly. So 20 and 50 aren't really that far apart. So yeah, the 14.3. Good. All right, what is the value in nanofarads of a 22,000 picofarad?
I would say C, Charlie.
So you said move it 3 decimals, right?
Yep. Nano to pico, 3 decimal points, places.
So Charlie.
Very good. What is the value in microfarads of a 4,700 nano?
D delta.
That's it.
Yep.
Same principle. Good. Which of the following components should be added to a capacitor to increase the capacitance?
C, Charlie.
Yep.
It's, you know, until you do this a fair amount, we kind of forget that resistor values behave the opposite of capacitor values in series and in parallel. But you're doing good with them here. Which of the following components should be added to an inductor to increase inductance? Inductors behave
Like capacitors, right?
no. Inductors behave
Like
like
resistors.
in series and parallel.
Yeah.
So if we want to increase the value, we would
E.
Yeah.
add in series because
Oh,
remember, it acts like a resistor, so we want to put it in series. All right, what is the inductance of 3 millihenry inductors connected in parallel? Now remember, inductors behave like resistors in series parallel. So they're equal values, so we take the value 10 and divide it by 3.
So C, Charlie.
yeah, C, Charlie, 3.3.
Good.
They're trying to get tricky with the henries and millihenries.
And I think
Yeah, they are.
and always remember in these, I think the good thing, you only get 1 or 2 questions in these different segments. So it's not like you're going to have all of these questions on, you know, the inductor, the resistor, all of that. So just hope you get the one you remember. All right, what is the inductance of a 20 millihenry inductor in series with a 50 millihenry? Inductors behave like resistors in series and parallel.
This would be just like
So
B.
C,
See, Charlie.
Because they
Oh.
add together.
because they're just like resistors. You add them up, right?
Yep. If inductors are in series, you add the values. If they're in parallel, you add the values. All right, what happens when an inductor is operated above its self-resonant frequency? Now, you kind of have to think about, this is an inductor. Think back to those photos we have of inductors being wire wound in a coil. If the frequency gets higher and higher, there's coupling between those wires.
It seems like it becomes capacitive because didn't you say there's some kind of residual capacitance or something like that?
That's exactly it. Yep.
Okay,
Very
yeah.
good. All right. What is reactance?
Well, we know it's always AC.
Yep.
Good. When
So
we're
I
talking
think,
about reactance or impedance, we do include the property of AC influence in the
yes,
circuit.
so C, Charlie.
I heard a no in there. I kind of like that.
The B Bravo.
I like that even better. Yeah, very good.
Oh, okay.
Yeah, opposition to the flow of alternating current. And by the way, that's true with an inductor or with a we have capacitive reactance, we have inductive reactance. Which of the following causes opposition to the flow of alternating current in an inductor? This one relates to the question right before it.
Delta.
Reactance, exactly, which is why you won't get both of those questions, I don't think. All right, what is the unit used to measure reactance?
Ohms.
Yeah, B, ohms.
B.
So whether we're talking about resistance from a carbon resistor or reactance from an inductor or impedance, the unit of measure is always the ohm. Which of the following causes opposition to the flow of AC current in a capacitor?
Reactance, right?
Yeah, you don't read in more than what's there. And of course, we're still on kind of the same section, so we've still got this theme of reactance. Okay, how does a capacitor react to AC? You probably need to remember that X of C equation, which is 1 over 2 pi FC.
My memory is saying A based on what we talked about.
Yeah, A.
Yeah.
Keep that memory. That's working. Yep.
'Cause
So
it seemed like it was opposite.
exactly. Yeah, I was just going to say, keep this in mind. So when frequency goes up in a circuit, X of C, or the reactance of a capacitor goes down. All right, what does an inductor, how does an inductor react to AC? Remember the equation, X of L is equal to 2 pi FL. So there's no reciprocal. So if you increase F or L, reactance goes up.
Yeah, I was gonna say D, Charlie.
Yep.
Delta.
D. So as the frequency of the applied signal goes up, X of L increases. Not the inductance value, but the opposition it provides to.
What?
Go ahead.
I'm sorry, what's the difference between A and D as far as how they're worded? Oh, decreases, increases. Okay, got it. Sorry.
Yep.
Well, that's a pretty good point because it's a subtle difference. You know, the other 8 words are the same.
Never mind. Thank you. Move, nothing to see here. Move along.
Well, see, that's a mistake I would probably make on a test. I read the responses too quickly. So that's a good point. When you're taking this, of course, I'm sure you will, but read each one through at least one time. You'll have plenty of time to take the exam. But yeah, something like that, you just think of, well, that's it, and you jump on it. Okay, what is impedance?
C.
C, because it's like a resistance for DC.
Yeah, exactly.
So which one?
C,
Charlie.
Charlie.
Okay. Yeah, I wish they would use the term total opposition because that's what impedance really is, total. Total meaning it includes capacitive and inductive reactance plus any resistance in the circuit. But yeah, it's the opposition of AC current in an AC circuit. All right, which of the following describes one method of impedance matching between two AC circuits?
Well, I remember this because the only thing I had an LC when we talked about it.
Right.
You insert an LC circuit to do the impedance matching. What is one reason to use an impedance matching transformer?
To maximize our power output.
All right, now what letter would that be?
B. B. Bravo.
Yeah, it is B. They use a little different term here, to maximize the transfer, which means the same thing you just said.
Yeah, I remember I in my mind I had it right, but I'm looking at the letters and going, wait a minute. But yeah, I remember as maximized to be able to match the impedance. I remember that. So back to your read the answers really carefully.
Yeah,
Yep.
that's got me all the time. Another comment there?
I was just agreeing, that you got to read thoroughly.
Yeah. Yeah, my career in school has been, I would often read these kind of things a little too fast if I was in a hurry. So, all right, which of the following devices can be used for impedance matching at RF frequencies?
Yeah, all of them.
Yeah.
Yeah, remember we said the length of transmission line, we also call a stub, and that's a matching transformer. And of course, the pi network, because it kind of looks like the pi symbol, and then the transformer. All right, what happens when the impedance of an electrical load is equal to the output impedance of the power source, assuming both impedances are resistive?
We're looking at D here, right? Delta.
Yeah, that's what I was
Yeah.
thinking.
Yeah, that's a pretty big concept for us in amateur radio, because we want to get as much power from the radio as we can up to the antenna and then out into the area. All right, what should be the impedance of a low pass filter as compared to the impedance of the transmission line into which it's inserted?
They should be about the same.
B. Yep.
Yeah, B.
Yep, very good. All right. What is the frequency above which the low pass filter's output power is less than half of the input? Remember that diagram, it had the pass band to the left and then it fell off the higher up we went, but there was a point at which we say, is that
C.
It was cut off, right?
Yeah, call off
Yep.
frequency. C. Charlie.
C.
exactly. And what's another name for that point with a number in it?
3
3
dB.
3 dB or something.
Yeah, 3 dB point. Good. All right, what term specifies a filter's maximum ability to reject signals outside of the pass band?
It's the ultimate answer.
Okay. Delta.
Yeah.
I remember that because it was to me it was a funny way to say it.
Yeah,
Ultimate rejection. Just thinking sports, ultimate rejection.
Right.
it's not what you would find in an engineering book, but it's the way they described it. So, all right, the bandwidth of a passband filter is measured between what two frequencies?
Gut says
A?
B. Bravo.
You know, B, and we haven't really talked about roll off, I don't think, at least in my section.
Nope, I haven't seen that yet.
So,
A?
yeah, A, because
A.
if
Yeah.
you remember that diagram,
Yeah, I remember now.
power points on the low end and the high end, and then the pass band in between it. Yeah, roll off is a good term, but not for here. And the pole zero, all of those other things we haven't mentioned. So, all right. Remember the term attenuation means loss. So what term specifies a filter's attenuation inside its passband?
A alpha.
Yeah, A.
Yeah, and that may seem kind of strange, but that is a common term because we insert this filter into the system. Well, that's an insertion loss because we put that in. So which of the following is a reason not to use wire wound resistors in an RF circuit?
Yeah, this is Bravo.
Yeah.
Yeah, Bravo.
Start to act like a capacitor in a way.
Right. And we don't know how that circuit is then going to perform. Which of the following is an advantage of the ceramic capacitors as compared to other types?
Show me the money.
Yeah, D, compared to low cost.
Yep. All right. What is an advantage of using a ferrite core toroidal inductor?
Strikes me as all of those are correct.
Yeah,
Yeah.
same here.
D.
Yep. Every one of those is correct. All right. What determines the performance of a ferrite core at different frequencies? Just think about the core itself.
C.
Yeah, it depends
Yeah.
on what the manufacturer of those cores made it with. So they'll make cores, for different frequency for different applications. Not how thick it is or its conductivity, but what's the mix of the materials. All right, what causes a voltage to appear across the secondary winding of a transformer when AC is applied?
Oh, these are all such good answers.
I'm thinking captive coupling, A.
Well, but we're not talking about a capacitor here. So you're half right. But because we're talking about a transformer, the capacitor side doesn't fit.
This is
I'm
mutual.
thinking mutual inductance.
Yeah.
We are talking about a transformer. A transformer is an inductor, and that means mutual inductance.
Yeah.
Perfect. All right. What is the conductor? No, why is the conductor of the primary winding of a many voltage step-up transformer large in diameter than the conductor of the secondary? Now remember, when we talk about conductor size, we're generally referring to its ability to handle current. The larger the wire, the more current, the smaller, the less current.
I'm thinking B.
B. Yeah.
Yeah,
To
B.
accommodate the higher
Yep.
amounts.
We would have higher currents on the primary than the secondary. All right. Now, goodness, they throw in RMS here. We'll assume they were RMS the whole time on my section. So what is the RMS voltage across a 500 turn secondary winding in a transformer if the 2250 turn primary is connected to 120? My best guess for you on this would be to memorize this one.
Out of memory, I think in C, but that's just
Yep.
out of memory.
No,
Yeah.
it's C.
It was like 26.6, and you said round up to 26.7.
There you go. Yeah, if your memory's that good, you'll be in good shape.
Just look at the questions and answers and memorize them.
Well, you'd have to have a really good memory for that. All right, what happens if a signal is applied to the secondary winding of a 4-to-1 voltage step-down transformer instead of the primary?
Times it by 4.
Yep. A.
Yeah, A.
And we talked about that, how the FCC is getting weird with that.
Yep. All right, what is the turns ratio of a transformer used to match an audio amplifier with a 600 ohm output impedance to a speaker that just has 4 ohms? And again, unless you want to get that equation out or equations, this is another one you may want to try and commit to memory.
Gosh.
I think A.
C?
I think A 12.2
Yeah.
to 1.
0.2 to 1.
Memory's gonna have to work on that one.
Yeah, that or go back and work through those equations we looked at earlier. All right. Now, I think that was the longer one. So do you guys want a quick break or go to the next one?
That's quick bio break.
Yeah.
All right. So when do you want to come back?
I say what, 10 minutes, guys?
Yeah,
All right.
sounds good.
Yeah,
So
good.
about
Perfect.
2:45.
46. 46, 45, somewhere there.
46. All right. See you then. Great. Thank you.
Okay, good deal. I will take over for a second while they are on break. So take this opportunity to get up and walk around, go get something to drink, take a bathroom break, whatever. This session's going pretty good. That was a long session, as he said. I think he said he has 3 more. I think 3 more, something like that. So we'll probably. I'm going to assume we'll go all the way till 5:30, which was the originally scheduled time. It was supposed to be start at 8:30, go to 5:30 with about an hour lunch in the middle. Of course, it was much shorter than that last week. They took a 2-hour, about a 90-minute lunch and ended an hour early. So we'll see how it goes today. Of course, I'll be here till the end. And these sessions will be replayable after the fact. The one from this morning, which was like 8:30. Well, I started about 8:15, but the actual session started at 8:30, and it went till about almost 1, something like that. So 4.5 hours, roughly. It is, assuming that it's processed on YouTube, it is replayable now. If it's not quite replayable yet, it will be shortly. YouTube's usually pretty quick about processing that. Can't wait till it's uploaded so I can watch at my pace. Yes, you can, like I said, you can kind of do that now. If YouTube has finished processing the stream yet. So when a live stream ends, YouTube does processing on the back end, and then it's replayable. Then once it's viewable by you, the viewer, it's replayable for the rest of its life until I take it down, which I'm not going to do. So the 2 from last week are up there now. You can go back and watch them as many times as you want to. And once again, the Hearst Amateur Radio Club did an in-person live session last November, about a year ago, that I recorded and put up on this channel last November. So it's been there for almost a year. So this question pool of general questions that is valid from 2019 to 2023 is now going to be on my channel in 2 places. It's been up on my channel for a year under a playlist called W5YI 2019 to 2023 General License Class Upgrade. There's a playlist on my channel. You can go watch 9 episodes. That's split into 9. Well, it's 3 different nights of class training that I split into 9 episodes, put on by the Hearst Amateur Radio Club last year in person, back when we could actually meet and do ham radio in person. So that's been up there for a year. This is new. Same question pool, same material, same everything, except it's different club, different teachers, different style, you know. And this one's being done live, so they're asking questions real time. So kind of so you've got options. You've got options now. You can go back and watch the one that I did from Hearst. You can watch the replays of this one if you weren't able to watch the entire thing live. So, yeah. Bill, thanks for being here. Darren, thank you for the super chat, $20 super chat. Really appreciate you being here today. He said he's still working on the technical series, but wanted to join today, let you know how much we appreciate you doing this. Looking forward to reviewing the recordings once I get caught up. You've enabled me to get a great head start, and looking forward to seeing you online when I get caught up. So thanks, man. Appreciate the support with the super chat. Appreciate you guys being here and chatting in the YouTube comments as well. Is there a particular scientific calculator that you all favor? I haven't had a scientific calculator since high school. I think I used a normal calculator. Of course, I got my first ham radio license in 1994. I think I used a normal everyday calculator on my test. Of course, that was a technician test. I took my general upgrade in 2014, 2013, 2014, somewhere in there. But I didn't use the scientific calculator there either, so I don't know. Anyway, that is that. What's the difference between ARRL and W5YI? They're the same question pool. So it's just basically like if I were to take a question pool and write a book, and then you were to take the same question pool and write a book, we wouldn't word things the same. We wouldn't word the lessons the same. The questions were all worded the same. The questions and answers are all the same because those are done up by the FCC and the ARRL, and they are shared with everybody. And places like W5YI put that together. But the questions and answers are all the same. The difference is in the presentation. So W5YI books, I think, do a little bit better job of explanation in the book. So a lot of people use that material. A lot of people in Texas use that material because W5YI is about 30 minutes that way in Arlington, Texas. So we like to use Texas-based guys, and we can fill out. Back before online testing was a thing, we used to give tests at the local ham radio clubs here, and everyone would take their paper test, and then the VE guys would take the test and drive them down to Arlington the next day and turn them in. So they didn't have to mail them. They didn't have to wait on the mail. Didn't have to do certified mail. They just drive them down there and drop them off. Online testing has kind of eliminated that need, but we've been using W5YI for years and years. And W5YI is doing online testing now. So it's just one of those things. It's 6 1/2 dozen the other as far as this study material is being done with W5YI. But if you have an ARRL book and you go through it, you can learn the test questions and answers that way. It'll work just fine. Nothing wrong with that. Bill says this is the most thorough class I've seen. It's great. Thank you, Bill. Appreciate that. Yeah, the guys are doing a good job today. Really appreciate them letting me live stream it and letting me share that information after the fact. All right. Okay, where are we now? Let's see. Good. Okay. So we've got about 3 minutes until 2 to 3 minutes until they get going again here. So hopefully you guys have got something to drink, took a break, get ready for the next session.
I was enjoying the sports background.
I was wondering where that was coming from. I didn't know if that was something coming from my side or what.
No, someone had their mic on. I'm like, yeah, this is all right for in between.
Oh, okay. Okay. Well, that works, I guess.
Well, I've got TCU in Texas on.
Oh,
I just turned the audio on. It's a
What's the score?
Well, it's 26-29 Texas, and there's 6 minutes left in the game. So,
What channel is it on?
Fox, Channel 4.
Okay.
So TCU hasn't done too much this year, but Texas is winning. They've got, I think they won 2, haven't lost any. Maybe get this one too. This COVID stuff has sure turned around a lot of sporting events.
that's for sure.
Yep.
Indeed.
Pardon?
Indeed.
I thought you said D. I'm like, where's the question?
Yeah, that's what I thought.
That's
I missed it.
Yeah, TCU has the ball, 1st and 10, but only 5 minutes left in the game.
Well, I saw before TCU was ahead quite a bit, and all of a sudden now, what happened?
So I guess you guys take the exam maybe on Tuesday, is that correct?
Yep.
Yep.
All right, very good. Well, you have a lot of privileges as tech, but when you go general, your world will really open up.
Yes.
I was taking a peek at the extra stuff, and I still may go through and try and do that, but man, this part's making my head spin. There was a reason that I decided not to be an electrical engineer in college after a semester of math. I'm like, I can't do this math.
Yeah, and the extra is probably it points close to that engineering curriculum. All right, well, are we all back? I've got 246. So
Good here.
okay, well, we said 246, so we'll start. This is a short section on grounds, but I do want to mention, including me, I have never met a ham operator who has not had issues with grounding. So while this one is short compared to the last section and far more practical, it is very, very important. So in fact, ARRL has a good book on grounding and bonding. So, all right, let's get started here then. All right, so we're going to do good grounds. All right, now if you receive an RF burn when touching your equipment while transmitting on, let me get rid of this one icon, on HF, assuming the equipment is connected to a ground rod, the ground wire has high impedance on that frequency. So what they're saying is, even though you may have a ground rod fairly close to your station, if you feel an RF burn when you're transmitting, you have high impedance somewhere in your ground system, and that high impedance allows a voltage to be developed across it, and that's what you're getting the burn from. So here is an example, or 3 examples. On the left, we have the best way to ground. So we've got the radio power supply, some accessory, maybe an amplifier. We've got a PC, and then across the middle here, if you can see my pointer, is a copper pipe or a flat piece of copper, which is made. That is terminated here on the right side, goes outside through the wall, through a window, whatever, to the ground rod. So the idea is you bring individual grounds to that ground strip or braid. You don't connect the ground of the radio to the ground of the power supply to the ground of the accessory, because you form a link there that can actually develop voltage across it. So you bring a short as possible wire down to the copper strip, this grounding bar from each device, and that goes outside. And then in the middle there, they show you how you should put that grounding rod in. I haven't priced grounding rods for a while. I imagine they're pretty high with copper costs. And then here's on the right, there's an accessory here of different ways to connect that wire that comes from your station, that single wire, out to that ground post.
So just a quick question.
Yeah, sure.
So what you're saying here is the ground that you have with the electrical plug on all your devices, that in and of itself is not good enough.
Correct. And the reason is you want as short a path as possible to ground. So on the photo on the left here, you see this where it says heavy strap or braid. That's probably only a couple of feet when you're in the best situation, when you can get to the outside ground that quickly. Otherwise, you could have, say, an impulse from lightning come in and ride right through your ground system, your electrical home grounding system, because you have that long, grounding, that third conductor going everywhere in your house. So that's susceptible to picking up energy before it can find a place at ground. So yeah, the answer is you want to do this in addition to any grounds, the 3-wire system you have in your home. Does that help?
Oh yeah, I mean I've heard a lot of this stuff, but I haven't heard this. This is certainly good information to know.
All right. All right, and the reason for the statement above where you have impedance on that wire is because at some frequencies, the ground wire is inductive and may become resonant at some frequencies. And when it becomes resonant, you'll develop a voltage across it, and then you'll get that RF burn. The burn isn't necessarily to worry about. It's the fact that you don't have a good complete ground. Using a low inductance ground wire will help reduce that. That's why they suggest heavy strap wire or braid. You want something that has a lot of surface area on it. The more surface area, the better off you are. And you could actually end up with a quarter wave length and have a good antenna right there in your ground system, which you don't want. All right, good ground. So symptoms of transmitted RF being picked up by an audio cable carrying at digital mode AFSK data signals between a computer and a transceiver could be caused by the Vox system. Vox system is that automatic keying where you talk and your receiver hears your voice and starts transmitting. That can cause problems if it doesn't unkey properly. Or the transmitted signal is distorted, which means it has spurious signals with it. Or the frequency connection may time out. And all three of those are correct. So when you have symptoms of RF being picked up by an audio cable, what they probably mean here is a headset or a speaker in your shack picking up these digital signals. And the RF signal is actually being rectified into an audio signal so that you can actually hear it. So it rectifies, it takes off that audio portion that we end up hearing, which in fact modulates the transmitter and feeds back again as RF. So you get this terrible loop when you have these things occurring because of the lack of a good ground, which sort of turns your whole station into a kind of oscillator, which again, you don't want because these are signals that are way out of range of anything you want and they don't carry any intelligence. So, and this is the point they made in the photos. Make sure to connect all grounds to a single point because you don't want a ground loop. So if you were to connect your radio to your to a speaker, to an amplifier, and then go to ground, you're going to have a ground loop. So the best way to avoid that is just to go directly to that ground strap and then out to your ground. And here are some good examples. On the left, you have a ground rod pounded right down into the ground. Good connection, copper on copper. You've got a good braid there, the second photo. If you look at that, it's very wide, so it has good surface area. The third one is a copper plate, very nice, pretty expensive, but it is a good way to ground. And then the third one is, I don't know how that differs in the front, or first one, but it's another ground rod pounded in to the ground.
That one plate looks pre-made where you get it and they're all just kind of just gives you places to put standard holes in, or is that someone drilling that themselves?
I don't know about this one, but I know DX Engineering sells a ground plate like that. And then what you have on each side, you can see the little feet on the left and right. Underneath are big red insulators. So wherever you mount that to, it's not electrically part of the ground. But yeah, and then they come with pre-drilled. So you just get nuts and bolts and you've got a lot of different connections you can make there.
Now, I have a quick question.
Sure.
What happens if your ham shack is on the second floor and you have no other place but the second floor to set up your ham shack?
Yeah, well, now you're into some issues. So the best thing to do is, again, run a good, if you look at the photo on the left, you can see that multi-strand wire going to the ground state. Do something like that, or the braid on the second one, and you're just going to have to run that, if you can, out a window, through a wall, straight down to the earth ground, and then put the ground rod in. But yeah, it is a bit of a disadvantage because now you have, a pretty long ground wire that could be susceptible to noise, to pick up signals, but it's your only option, other than to move the station to a second floor. But some people live in an apartment and that isn't going to work. So you have to, in amateur radio, you find you have to work with what you have, and that's kind of your best option there. And on the bottom, they show different examples, copper taping there, strapping. Those are all very good. Save your pennies, those are expensive. But again, for good grounds, that's what you need to have. And any metal enclosures that people have with their station should be grounded to make sure that voltages cannot appear on the chassis of those metal enclosures. Here's another example of a transceiver, power supply, antenna switch. So they have the braid going down to a copper pipe in this example. And then on the far right, they have braid going outside to that copper ground rod. And then there's a little bit better photo, I guess, on the right-hand side here to show you station grounding. But even with that 3-conductor wire system there they still go outside and pick up that close ground connection. And before I push the button again, TCU leads 33-29 with
Wow.
a minute and a half. All right, a resonant ground connection could cause high RF voltages on the enclosures of station equipment. That's That's the same as the earlier example. When you have a resonant ground connection, you have the possibility of getting that RF burn or high RF voltages on any of these enclosures up here without proper grounding. So that's what I said. I've never run across a ham that has set up a station and it has not dealt with grounding issues at one time or another.
Quick question, does resonant mean not very good, or?
Well, it means it's a resonant system to frequencies that you might be using. So if that's the case, a resonant circuit is going to really respond to and capture that signal.
Oh, okay.
And it's not a signal you want. It might be a signal from a Wi-Fi router or something else that will cause you problems. And of course, the theory is you want to keep the station's ground wire as short as possible, but like was just asked, if you're on the second floor, not much you can do about keeping it short. And a good way to avoid stray RF energy in a amateur station is to make sure you have all of those grounds going back to that common copper pipe. All right, bypass capacitors might be useful in reducing RF interference in audio frequency devices. So bypass capacitors, they would allow interfering RF energy from getting on your audio device lines, like a headset or a speaker line. And the idea is that and I'm going to use the center here mostly. The two on the right are good, but those are for circuit analysis. The bypass capacitor provides low impedance, low resistance to the high frequency noise, but yet lets the other information to pass through to wherever it's going. So if you notice here, they show what the scope might look like, oscilloscope might look like without a capacitor, all that noise here, and then with a capacitor, it's probably down 20 dB. So it's a good way to prevent that from it bypasses it right to ground. And then placing a ferrite bead around the cable could reduce RF interference caused by common mode current on an audio cable. So these are 3 examples of ferrite beads used on all sorts of different cables. And these are pre-made by folks like DX Engineering and others. And you just snap those on microphone lines, speaker lines, and they will help reduce our RF interference by blocking what they call common mode or current on an audio line that's coming in when it really shouldn't be.
Used to see those all the time on older cables, but I think they got too expensive and they just kind of got rid of them, or maybe had better shielding on them.
Or it could be that they've gone to digital devices and don't need it as much as analog. All right, so distorted speech is heard from an audio device or telephone if there is interference from a nearby single sideband phone transmitter. Could be an AM station or CB coming in. On and off humming or clicking is one effect of a nearby CW transmitter may have on an audio device or telephone system. Some of these things we don't have much anymore, like TV. Most people are on cable. Most people use cell phones, so we don't have that side of the problem anymore. Arcing at a poor electrical connection can certainly cause interference. Arcing creates what we kind of call white noise, and that's electrical noise all through the bands. So you want to regularly check, make sure your antenna connections are tight. Power, especially DC power connections, they're famous for getting loose and arcing or creating resistance and not making a good path. Hopefully we don't have any outlet connections.
Yikes.
Yeah.
Yeah. That could happen actually with if a screw becomes loose and there's arcing over time, that will heat up actually pretty quickly. So, and
That's
on
a scary attic.
yeah,
Sorry.
I wouldn't want to crawl through that space.
Me neither.
Yeah, or the one in the center. I don't know where he got these photos.
No.
All right.
Right before houses burned down.
Yep. All right. Receive interference receive interference in a radio installed in a vehicle may be caused by battery charging system. That's very common. The fuel delivery system. That's again very common. The vehicle's control system that can cause issues. So if you're mobile, that can happen. Or if you live close to a thoroughfare and you have any cars, vehicles come by with those, you might pick those up momentarily. And then a steady raspy carrier that only disappears with the engine off. Whistle sounds that can change the pitch when the engine revs, that's an alternator issue. Ticking sounds all over the band, electronic fuel pump. And that's it. So let's look at the questions and see what we've got here. So what might be the problem if you receive an RF burn when touching your equipment while transmitting on an HF band, assuming you have good grounding?
D delta.
Yeah, D delta.
Yep. Ground has high impedance that allows a signal to be developed across that impedance. All right, TCU 33, Texas 31 final. All right, which of the following can be a symptom of transmitted RF being picked up by an audio cable carrying AFSK data between a computer and a transceiver?
Every one of them.
Yep, D.
E.
Yep. Go through all of those. How can a ground loop be avoided?
Delta.
Delta.
Yeah, delta.
Yeah.
They didn't have the don't go on the second floor answer.
Yeah. Well, actually, the second floor still, you know, the key here is single point. So you bring all your equipment to that copper pipe. The second floor becomes the issue when you have to then take that copper pipe electrical connection out the window or through the wall down to the ground. So even the second floor can get, the single point connections. It's just that length of wire going to the first floor. All right, what would be the symptom of a ground loop? What could be a symptom of a ground loop? I'm sorry, somewhere in your station.
I'm thinking A.
Yeah, A.
Yeah, A.
Yeah, because in all of this, we certainly didn't mention SWR. So what must the metal enclosure of every item of station equipment, why must the metal enclosure of every item in a station be grounded?
Delta.
Yeah,
Delta.
Delta.
Yep, you don't want those hazardous voltage to appear across the chassis. What effect can be caused by a resonant ground connection?
D. Delta.
Yeah, Delta.
And if it wasn't
Well,
Delta,
I mean,
D?
C looks good too.
yeah,
Yeah, it does.
you develop that high F voltage across that resonant ground system because it's tuned, the resonant means it's tuned to a frequency, it's resonant at that frequency, so it's picking up that signal.
Yeah.
All right, which of the following might be useful in reducing RF interference to an audio device?
Bravo.
Yeah,
Yeah, Bravo.
bypass capacitor. Take that energy, that signal you don't want. The capacitive reactance is low at that frequency, so it passes it right to ground. All right, which of the following would reduce RF interference caused by common mode on an audio cable?
Well, I'll go with A, but B looks
A.
like fun.
Yeah.
Well, B, theoretically, you could get away with trying to get rid of common mode, but the ferrite, the inductive part of that, A, is far more practical. So taking a ferrite choke that is really set for that frequency is best. What is the sound heard from an audio device or telephone if there is interference from a nearby single sideband phone transmission?
Yeah, they told us C, right?
Yeah. Yep, and it's distorted, one, because it's single sideband, it can't pick up all of the information, so it really sounds goofy and causes problems. All right, what is the effect of an audio device or telephone system where there is interference from nearby CW transmitter?
I think I like C, Charlie.
Yeah.
And if you didn't like C,
A.
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 yeah,
Well, I like C. It's chirpy. I like chirpy.
well, for the test, like A.
Okay. Point taken.
Yeah, it's the on-off. CW is on-off. So you get some kind of interference, typically the humming or clicking. So
But when you can start sticking code on the humming, then you know it's bad.
yeah. All right, which of the following could be a cause of interference covering a wide range of frequencies? And I referred to this as white noise for a particular problem.
C.
Yeah, when you have
Yeah, C.
when you have arcing, you there's a huge spectrum of electrical energy produced. In fact, power companies often have this. They'll have a poor connection at one of their transformers, and gosh, does it wreak havoc on ham radio folks. All right, which of the following may cause receive interference in a radio installed in a vehicle?
D, all of them.
Yep. Every last one of them.
Yep. This is why I never put an HF radio setup in a car. You really have issues like that. So I stick to VHF and UHF in the car. All right, ready to go to the next?
Yep.
Yep.
Let's do it.
So that's good grounds. All right, this one, I hope I'm doing these right. HF antennas. This one's a little longer, but I don't think as meticulous as that first one. So HF antennas, 32 feet is the approximate length for a half-wave dipole cut to 14.25. And a half-wave dipole, by the way, is one of the most popular HF antennas out there. Inexpensive, works great. So you'll see a lot of information once you get into antennas and stuff about that. You calculate the half-wave frequency in feet. In order to do that in megahertz, you simply divide by the constant 468 divided by the frequency. So you have 468 as a constant divided by, in this case, 14.25, and that gives you the half-wave length. And that's rounded to 33 feet. The approximate length of a half-wave dipole antenna cut for 3.55 megahertz, 80 meters, is 131 feet. Same thing, same constant, 468 divided by the frequency, or 132 feet. And then you just adjust it by a fraction of inches once you get it cut.
So am I
Here-
guessing at that frequency, it's a less popular antenna because of how unwieldy it becomes?
That's a good point. It would depend. So there are limitations. If you live in an HOA, this is out the window pretty much. Yeah, so the lower the frequency, as you know, the wavelength becomes longer and longer. So that, and if you live on a small lot, then it becomes a problem unless you go with a vertical. So yeah, it does cause, you know, the band you're on, the meters do cause an issue. So an example of the dipole is in the figure here. The total length is half wavelength, but each side is 1/4 wavelength. All right, an advantage of a horizontally polarized as compared to vertically polarized HF antenna is lower ground reflection losses. So I'll let it draw its picture here. So here's an example of, oops, my pointer. So you've got a line of sight signal here. You've got ground reflection. So you've got signals coming off of the antenna, hit the ground and reflect. So an advantage of horizontally polarized antenna is you have lower ground reflection losses. So the fact that there's energy going here as well as here takes away from the total energy. You'd rather that, in this case, the line of sight be directly across here. This comes in out of phase of the regular signal and is a reduction. All right, and then you have RF energy is lost each time the radio wave is reflected. So you don't really want that. And the amount of energy lost depends on the frequency, the angle of the incident, the angle that that energy is hitting the ground, any ground irregularities. Here they have flat ground, but that's not always the case. So if you hit a building or a side of a mountain, it's going to reflect a different direction. Then it doesn't even get to the source you're trying to get to. And of course, the electrical conductivity of the point at which it hits the point of reflection. So whatever that conductivity is really controls about how much signal is being sent back. Now, the NVIS, or the near vertical incidence skywave propagation, permits short distance, medium frequency, or HF propagation using high elevation angles. Here you lower your antenna, you'll have a higher elevation angle of radiation, and this causes the NVIS shorter than normal skywave communications, but it can be useful in certain applications. So here's an example in the chart. The higher up the antenna, they show it here in meters, will depend on how the signal radiates from that NVIS signal. So these can be interesting for shorter distance communications, and also you're not using horizontal where you might need greater land capability. All right, horizontal dipoles placed between 1/10 and 1/4 wavelength above the ground, the height, will be most effective for short skip communications on 40 meters during the day. So for example, I use kind of a horizontal dipole here, and I do a fair amount of communications on 40 meters during the day. So I'm good for Texas and the surrounding states for that. Antennas that are used for DXing, meaning you're going across the ocean or way down south, should have lower takeoff angles. You don't want those hitting anything before they really get a good distance. And one thing that affects the takeoff angle of an antenna is its height above ground. So to have further communications, raise the dipole lower to receive the first hop. So you'll see these DX stations with very tall antennas. And here's an example of a portable half-wave dipole. And here is the radiation pattern. So the area within the red maroon circles here, this is the area your signal would cover. Not too much east or west, left or right. So you could change the orientation of that antenna if you wanted to turn that pattern. And then depending on the height of the antenna, you get all of these different radiation patterns. And here they're just looking at the one lobe. But you can see the different colors depending on the different antenna heights. And again, you experiment with this and see what's most useful for whatever your application is. All right, as the antenna is lowered from 1/4 wave above ground, the feed point impedance of a half-wave dipole antenna steadily decreases. Now, this is a practical question or idea, because you can control the impedance just by the height of the antenna. You can also control it by the lengths of the wire, but this is another way to influence the impedance. So the antenna height directly affects the feed point impedance. And remember, the reason this is important, we want the impedance of that feed point to match the impedance of the output of your transmitter. And the output of your transmitter will be 50 ohms. So you want to match that 50 ohms to your antenna for maximum radiation. And the feed point impedance of a half-wave dipole steadily increases as the feed point location is moved from the center towards the end. So you'll hear we talk about the figure in the top is called a center fed. The next photo right below is an off-center fed antenna. And again, you do that to shift radiation patterns and impedance. A lot of experimenting on this part of amateur radio is the antenna system. And a common name for a dipole with a single central support is the inverted V. This is what I have. and is one of the most popular antennas. It can be a homebrew, it can be commercially purchased, but they can be just very effective. I've talked all over the world when the bands are good with an inverted V. All right, the feed point impedance of an end-fed half-wave antenna is very high. So this figure shows us we have a dipole, we have the feed line that has a much lower impedance. If for whatever reason your system is looking for a much higher impedance, then you go with what we call an end-fed, and then you use a transformer to match that back to your radio. So a resonant dipole has an impedance at the center of about 72 ohms, not too far from 50. The end-fed, however, can have 2,500 ohms. So you need a transformer or balun to really get back to your radio. This is the radiation pattern of a dipole antenna in free space. So again, and you keep seeing dipole references here because it's one of the most popular antennas. Low cost, very effective. So this is the plot or the radiation pattern. In this case, it would be north and south by the way the wire, which is east and west here. Excuse me, that dark black line would represent the actual radiating wire, the antenna here. And depending on what you do with that, you can get all kinds of different patterns. We kind of saw that in an earlier slide. Another thing that's kind of good about, or can be good about this, is reception and transmission are very weak over in the 45 down to 125 degree area, and then the same on the opposite side. You don't transmit anything really to speak of over here on the margins, and you don't receive much. So if you happen to have some kind of noise source over here or over here, this antenna would really null out a good portion of that noise because it just doesn't hear it because of its characteristics. So the maximum direction radiation from a portable or mobile VHF, UHF halo antenna is omnidirectional in the plane of the halo. So omnidirectional means it radiates 360 degrees. Now, antenna height can affect that radiation pattern. Excuse me. So the horizontal or azimuthal radiation pattern of a horizontal dipole HF antenna, in that if an antenna is less than a half wavelength high, this pattern is almost omnidirectional. As you change the height of that antenna, you can create different radiation patterns. So the energy is where these blue sections are. The first one is quarter wavelength, where you have 360 degrees. But then you start breaking the pattern. So in the center here, you have no reception to speak of or transmission, no signal. And in here you have multiple lobes on each side. So this is why I say there's a lot of experimenting that goes on with HF antennas. So omnidirectional in azimuthal best describes the radiation pattern of a quarter wave ground plane vertical. So if you notice here, there are two different radiation patterns, one in red and one, I guess that's black. Vertical radiation pattern showing elevation of a signal from a horizontal dipole at a half wavelength above ground.
A quick question.
Sure.
These are all views from an oscilloscope.
These
right?
are, no, that's a good question. These would be more likely generated from a computer that can model antennas. So what you do is you tell the computer what the antenna is, the length, the orientation, all of that, and it will plot this. Now, to actually take and plot this, you'd have to, it would take a long time. You'd have to have a field strength meter and walk all this distance, and every foot or so make a designation of what the signal strength is, which means it's not practical. So
Okay.
yeah, and an oscilloscope wouldn't pick this up. It's a
I
good
was just trying to figure out how to what this means, but that answers my question. Thanks.
So, but even better to that question is if you look at like the ARRL handbook, they will show you all kinds of different antennas, and then they'll show you these radiation patterns. So you'll know ahead of time that if you build it to those specs, you know, that's the pattern you should expect. All right, the approximate length of a quarter wave a vertical antenna cut for 28.5 megahertz is 8 feet. Again, you calculate that for the constant is 468, but the frequency has to be in megahertz to do that. So in this case, it's 28.5, 16.4 feet. Quarter wave antenna should be 1/2 the wavelength. So that is that. So you've got 16.4 over 2 or 8.2 feet, which they round to 8 feet here. Let's see. Now, this is a vertical antenna photo on the right. We just see the base of the antenna right here. This is a plate that is set down before you put the antenna in, because your antenna is going to be pretty tall. But what they're creating here is what we call a radial system of wires. It's a ground-mounted vertical, and those radial wires should be placed on the surface, which you see here, or just a few inches below ground. And the reason somebody might put it below ground is this antenna happens to be in an area where people are going to be walking or mowing the lawn. So if you're going to do that, you'd have to trench each one of these, which is a lot of work. Most people will try and cut the grass real low, put out their radial field, and then let the grass grow up around it. And then the mowers never set low enough to pick these up. But these go out probably 20 to 30 feet all around. And there's the ground wire plate system. And there's a kit where you actually get a plate and then the wires that you string out as you see in the photo above. Bidirectional antenna would be the best HF antenna to use for minimizing interference. Another name for this is a beam or a Yagi. And the reason it's best for minimizing is, I don't know if they have a pattern here. Let's look. It has very high gain. It radiates in one direction. They call it a Yagi or a beam. It doesn't look like they're going to give us a pattern, but this radiates essentially in one direction. So it's very good for minimizing. And the other thing is, you're taking most all of your energy from your transmitter to the antenna, which transmits that energy in one direction. So these are very popular in a lot of different uses. And here's an example of it. You've got directors. Excuse me. You've got drivers and reflectors here. So it sends the energy off what they call the maximum direction. So it sends the majority of that energy in that. And then on a rotor, you can move that all around. The approximate length of the driven element of a Yagi is a half wavelength. And then they vary on the director and reflector, but they show you here on the photo. Increasing the length of the boom, which is the device that connects the reflector, the driver, and the driver, the reflectors all together. So the length of that boom determines the gain of the antenna. So the more directors you add, you'll increase the gain, meaning you'll send even more, you'll reflect more energy in that direction where you want it sent. And that's called the major lobe. Well, here's a good example. All right, so they've got the pattern. The pink here on the right really shows, if you can see most of the energy goes in one direction. And in fact, this is a very tight Yagi. So it has a very neat, very narrow beam width. So a lot of energy goes there. You do have some side lobes down here where energy goes out, but not much. So you generally don't count on this, these patterns here. This is the main one here, the main lobe or major lobe of the directive antenna is the direction of the maximum radiated field strength from the antenna. Now, the front to back ratio of a Yagi is comparing the power transmitted in the forward direction up here compared to the power reflected in the backside, what we call the backside of the antenna. So the front to back ratio of a Yagi antenna is the power radiated in the major radiation lobe compared to the power radiated in exactly the opposite direction back here. There is some power directed here. You'll notice it's much shorter distance and certainly not a uniform lobe. In a Yagi antenna design, the following variables that could be adjusted to optimize forward gain, also front to back ratio, also SWR and bandwidth are the physical length of the boom, how far it goes out physically, the number of elements on the boom, the more elements, the better and the tighter that radiation lobe becomes. And then the spacing of each element along the boom. And all of these impact those features of the Yagi. Very popular antenna. They can be expensive, but they do have high performance. And here is kind of the top end. This picture on the bottom, he's got 1, 2, 3, 4. Looks like he's got 4 Yagi antennas stacked, and a couple of them are pointed in the same direction, a couple are not, but they can be rotated together or individually. And this is a serious station here. Also serious money.
So in this case, he's got like 4 Yagis pointing all 4 directions, so it becomes omnidirectional in a way.
He's got 1, 2. See, this is a boom. This is a boom, 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 and boom. So he's got 1, 2, 3. He's got 5 different Yagis. Now, I can't tell from the photo what the front and back is. If we had a bigger picture, we could look for the larger, we could look for the driven element or the reflectors. But yeah, he's got 5 here. No telling how tall this tower is. But this is a serious person who does what we call DXing. They're not talking to the friend over in Pennsylvania. They're talking to somebody in Japan or Germany.
I was thinking more hypothetically, if you could 4, kind of have a strong signal in all 4 directions if you had 4 different Yagis and not have to rotate it. Just what I was thinking.
Yeah, you could do that. There's a lot of different things you could actually do. People will stack these so they'll operate 2 booms together, same frequency, same direction. Maybe the other one is 180 degrees out of phase with the lower one. So like you said, they've got great signal strength one way from one antenna and the opposite way from the other. So when these are on individual rotors, you can do all kinds of things like you just said. It gets very interesting and creative.
Okay, thanks.
All right, larger diameter elements increase the bandwidth of a Yagi. So just think larger diameter elements, bigger diameter, increase the bandwidth. An advantage of using what's called a gamma match with a Yagi antenna is it does not require that the driven element must be insulated from the boom. So this gets into how they're made. So if you are using a gamma match, then all of these elements can touch the boom. If you're not, then you want the driven element to be electrically isolated from the aluminum boom it's connected to. So you don't want any electrical connection there. So again, depending on your application, your needs depend on how you approach the construction of the antenna. And here is an example of, this is the boom right here. This is the feed point, and this is a gamma match. So they're feeding the antenna here. If you can see my pointer, it goes up here. I think here's a drawing of it. So this is on the right side, you've got an adjustable clamp here for SWR. You've got the feed point down here. You've got the boom right here. The boom horizontal view doesn't help too much, I don't think. And then you've got your regular SO239 here in the gamma match. And of course, this all then goes way up on a tower somewhere. A beta or hairpin match is a shorted transmission line stub placed at the feed point of a Yagi antenna to provide impedance matching. So if you remember back in that other PowerPoint, we talked about a transmission line could be a transformer, and we often call that a stub. Well, here's an actual use of it. Let's see if he's got a photo. So here is a beta match. I'm not seeing the shorting. Oh, it's right here. Yeah, so up here is their hairpin match that they're talking about here. So you can match your impedance of the antenna precisely. And then right here is the SO239 to come back to your transmission line. And then they've got a 1-to-1 bowing. And here's an example of it on the other side where you can adjust that again to match impedance. And a third one laying on the ground to show you a little bit better. And again, you can adjust that to match. When you have antennas stacked like we saw in the other photo, they can interact with each other and change the impedance and the SWR. So you want these adjustments here, that, like right here, where you can adjust that when you have it several feet off the ground to get it just where you want and then haul it up. And a fourth example. Kind of a hair, they call it a hairpin because well, you guys are probably too young to remember the hairpins, but it kind of looks like that. All right, an advantage of a vertical stacking of horizontally polarized vertical antennas is that it narrows the main lobe. So here's where two examples, this one's horizontal polarization and this one's vertical, where you use two for either one. You don't, in this application, use horizontal and vertical, but using two of those, you narrow the main lobe in that radiation pattern. So you double the cost of the antenna, but then you get really better performance. Much narrower beam, which means your signal goes out further. And Yagi antennas spaced vertically at a half wavelength apart, typically at approximately 3 dB higher of gain than a 3 element. So let's see, Yagi antenna spaced vertically. Oh, so when you're using multiple antennas stacked about a half wavelength apart, you can get a 3 dB gain. And remember earlier, 3 dB gain, you're doubling your power. Without doing anything to your transmitter, you're just getting that much more out from your antenna. than if you use a single Yagi. All right, the primary purpose of antenna traps is to permit multi-band operation. So the yellow part of this diagram shows 3 traps on each side. That's so the antenna can be used from 10 meters up to 40 meters. And then the photo actually shows 2 different traps. The one right above where it says TC, that's actually a covering that goes over this trap, which they have below. They slid the covering off of that, protects it from the weather, but it lets you see what it looks like. So it's really an inductor. And let's see, a disadvantage of multi-band antennas is they have poor harmonic rejection. So the advantage is you have one antenna system that covers many bands. Disadvantage is they don't reject signals well. Because they have that characteristic of many bands, they're going to pick up a lot of different harmonics. Here's an example of a trapped antenna, not too good a photo, but it's on the roof of somebody's house. And right at the base here, you can see the top of the tower, it would have a rotor on it. So they could change that direction very easily.
Quick question.
Sure.
So with the traps, is it something that you can set inside? Is it something that just lets them all 3 bands work, just depending upon where you're tuning? How do you differentiate? Does that question make any sense?
Well, let me try. So the antenna in the yellow here
Mm-hmm.
would, let's say it's a commercially purchased one. So you would know going in, you're buying an antenna that covers 10, 15, 20, and 40 meters. So it comes with these traps, and they're actually out on the wire that's way up there in the air. And there's 3 on one side and 3 on the other side. The one here are traps, just like in the antenna on the bottom. This one has 2 traps, so one on each end of all 3 elements. So they're manufactured that way, you build it that way. Does that answer the question?
Well, I guess what I'm asking is, are they designed to use all the, like in the yellow one, can they use 20, 15, and 10 as is, or do you have to do something physically to change it to be usable for 20, 15, or 10 meters?
No, that's a good question. So if you look here, this transmission line coming out, this is a center fed dipole. So that would come into your radio, would actually come into an antenna tuner. So the only thing you would do is you would switch bands on your transmitter, and then you would, your antenna tuner would just make sure it has good SWR. So there's no need to go back up to the antenna and make any changes.
All right, that's what I need to know. Thank you.
Yeah, good question. All right, one disadvantage of a directly fed random wire antenna is that you may experience RF burns when touching metal objects in your station. So random fed antennas are just like the name, random lengths. To match that random length to your transmitter, you must have a tuner. And because of this, there will be high RF levels in your shaft when you are transmitting. So I've never used any antennas like that. Now, an antenna coupler is often used to enable matching the transmitter output to an impedance of other than 50 ohms. So there are couplers out there. There are transmission lines that are other than 50 ohm impedance characteristic. Here's an example of an auto tuner, meaning when it senses the frequency, the transmitted signal, it will automatically, through a series of relays, adjust inductors and capacitors to match your radio to the antenna. They work pretty slick. And then when they do match it, they remember that. So if you go to another frequency and then come back to the original frequency, As soon as you transmit, it remembers those settings and goes right to it. So it sets it in a fraction of a second. Another type of tuner, which work very well but not as fast, are what we call the manual tuners. MFJ makes a whole line of these. They work very well. So, and they're manual are much less expensive than the auto. So just depending on what a person wants to spend will depend on where they put their money. And here's an example of the tuner schematic where it rotates between different values of inductors. And then you've also got variable capacitors here, which are these controls up here. If this were an auto tuner, this switching would be done by little micro relays for both inductors and capacitors. It sounds like a little real light machine gun when it's first tuning because it's going through and finding the best setting.
Yep, I heard that in my father-in-law's shack.
Yeah, pretty cool. All right, the term dBi and dBd when referring to antenna gain means that dBi refers to an isotropic antenna and dBd refers to a dipole. So these are two different ways to reference antenna gain. Some manufacturers use one, some use the other. dBi is a measure in decibels referring to an isotropic radiator. That type of radio or radiator really doesn't exist, but it's a theoretical use. And its gain would be measured in zero if it did exist. dBd refers again to the use with a dipole. The dipole antenna has a gain of 2.15 dB over the isotropic radiator. And it has a gain of zero when measured in dBd. And isotropic radiators are used as a reference. They are theoretical only, just used again as that reference. So here's the isotropic radiator. You know, what direction does it radiate here? Equal power radiated in all directions, meaning equal potential electric field at constant differences from the center of the sphere. Comparing the gain for the same antenna between the measure of dBi and dBd will show that dBi gain figures will be 2.15 dB higher than the dBd gain figures. And this is why some manufacturers use dBi gain, because it gives them a 2.15 advantage in gain. So if the person reading it doesn't realize that it's dBi and not dBd, a gain figure, they think they're getting a higher gain antenna when in fact they're not. I bought a antenna, I still have it. It's a Yagi on the roof. And I thought, gosh, that gain's pretty good for a compromised beam antenna. And then I realized they were quoting the gain in dBi units. So again, the isotropic radiator is a theoretical point source, has no preferred direction of radiation. It's equal in all directions and centered at that point source. Now, nulls in the radiation pattern of a small loop antenna, and by the way, loop antennas are becoming big. Tom taught the section this morning, and my gosh, he's an expert on this stuff. So he's real good with magnetic loops. But less than a 1/3 wavelength circumference. So here's a photo of one. They're just nice to have. They're small, very effective. I think we were on the radio the other night. I think he said he was talking to somebody in Brazil on one that was just like this in his backyard, you know, not up on a big tower or anything. So they're very effective, low to the ground. They can be, you know, if you live in an HOA, they can be easy to hide. Now, the combined vertical and horizontal polarization pattern of a multi wavelength, the horizontal loop antenna is typically omnidirectional with a lower peak vertical radiation pattern angle than a dipole. So again, there are times when you might want to use a dipole over this, or times when you want to use a loop. Again, it kind of comes back to where you live, what space you have, just a lot of different reasons for these different types of antennas. All right, the elements of a quad antenna are square loops. Each side of a quad antenna driven element is approximately a quarter wavelength, so you end up with a full wavelength. Each side of the cubical quad is a quarter wavelength. So from the driven element, each side is 1005 divided by frequency in megahertz divided by 4, because we want a quarter wavelength. And here's an example. I've never done anything with this, but I've known folks that do. So you've got the driven element reflector separated by some distance here by a boom. And then you get a radiation pattern, in this case, off to the right. And then there are what they call spreaders here to position the 4 quadrants of this. Never really looked at these, but there are folks that do. And horizontal polarization feed point there on the left, lower left. And the forward gain of a 2-element quad antenna is about the same as the forward gain of a 3-element Yagi. The advantage here is you have smaller space for this type of antenna compared to the Yagi. And these tend to be easier to build than a Yagi, because you've got to have all of that aluminum, the spacers and everything. So the advantage here, especially as a homebrew, would be this antenna. The reflector element must be approximately 5% longer than the driven element for a 2-element quad antenna when the antenna is meant to operate as a beam antenna, assuming one of the elements is used as a reflector. Now, there's a special type of Yagi, a log periodic antenna. In a log periodic antenna, the elements' length and spacing vary logarithmically along the boom. You may have seen one of these as years and years ago as a UHF antenna, a log periodic. They tend to be very long, kind of hard to tell in this photo. But they are spaced logarithmically along the boom here, and can be very effective. You know, if you're into satellite communications or things like that, where you need a lot of energy in one point, these are the way to go. Here's another example, a little clearer photo, actual photo on the right side. And your feed point is right down here. And the one in the center, this fellow's log periodically is huge. We can't even see most of the antenna in the picture here. But as you get into this, if you subscribe to ARRL, you'll see articles where people have just these enormous antenna systems. The gain of a log periodic antenna is less than that of a Yagi, but an advantage of the periodic is its wide bandwidth. So you don't have narrower frequencies to contend with in a log periodic. And again, whether or not you need that would just depend on what your application is, which is why many stations have several different types of antennas. All right, another type of antenna, really a receiving antenna, is what's called the beverage antenna. Is a directional receiving antenna for low HF bands. And it's generally not used to transmit because it has high losses because of all the copper wire involved. But it is good for seeing what's out there on the frequencies. See, maybe pick what frequencies you want to transmit on. Here are some photos of some actual ones. And again, on the bottom there, it shows you've got a transformer in here. You've got your 50 ohm coax. This goes to the radio. That's the schematic symbol for the coax. You've got a 9-to-1 transformer to match this beverage antenna to 50 ohms. All right, now efficiency of an electrically short antenna limits HF mobile installations. This is another reason I don't do mobile HF is when you get to HF frequencies, your antennas have to be pretty short, relatively speaking, so you really compromise efficiency. And it wouldn't be possible to put a full quarter wave 75 meter antenna on a mobile. 40 meters is possible, but lower frequencies, you really can't get anything that's efficient. And anything for frequencies below 40 would not be good at all. Now, this fella has some, well, 3 cars. This Land Rover is kind of interesting. He's got all kinds of different antennas. Most of these are VHF and UHF or higher. This is an HF antenna. This black car here that we refer to as a screwdriver because it goes up and down to adjust SWR. And this bottom one, the white car, has a big loading coil and then what we call a whip on top for some HF frequency. One disadvantage of using shortened mobile antennas as opposed to a full-size antenna is the bandwidth can be very limited. So it's a challenge, although there are people who love the challenge of mobile HF work. And I've talked to people here in Keller all across the US and they're mobile on HF bands. So it does work. As I just mentioned, the screwdriver mobile antenna adjusts its feed point impedance. A lot of times these are motor driven, so they can adjust it from inside the car. And they are adjusting the loading inductance so they can match the impedance, again, for maximum power transfer. And here's an example of those. So there are some manual types out there. Those tend to be much less expensive. And then the motor on the right side, motor driven, work very well. But again, you pay for what you get. And there are different antennas for the different bands. You can see the 4 different ones here. All right, capacitance a capacitance hat on a mobile antenna is a device used to electrically lengthen a physically short antenna. So if you remember, mobile antennas on HF tend to be physically shorter, and that's a disadvantage. But what is used is the capacitance hat to not physically, but electrically lengthen the length of the antenna. So here are some examples of different capacitance hats that are out there. All kinds from different manufacturers, homebrew, they're just, and again, that ARRL antenna handbook is a good reference for these kind of things. And the purpose of a corona ball on an HF mobile antenna is to reduce high voltage discharge from the antenna. They dissipate static buildup from the movement. So a lot of people would think that would keep you from poking your eye out, but it's really meant to help dissipate static buildup. Because when wind or air moves across an antenna, it generates electricity on it. So you have to be careful of that. All right, the antenna and feed line must be connected to an antenna analyzer when being used for SWR measurements. So there are devices out there. MFJ has a whole range of those antenna analyzers, very good. Comet has a line of analyzers as well. And they're used to measure SWR and different characteristics of antennas and actually feed line too. A use for an antenna analyzer other than measuring SWR of an antenna system is determining the impedance of an unknown cable or unmarked coax cable, which you may think is 50 ohms or 75 ohms, but you're not sure. But devices like this will let you measure that and see what it really is. Strong signals from nearby transmitters can affect the accuracy of measurements when using these analyzers. So you have to be careful of that if you're out, say, in a field situation and you're near a large transmitting site of some type. But I use one here at the house quite a bit and don't have any interference issues. Now, another device is a field strength meter, may also be used to monitor relative RF output when making antenna and transmitter adjustments. I've not used one of these, but they've been around forever and they work very well. I just found the antenna analyzer to be more helpful for me. But as I mentioned before, if you wanted to physically measure the radiation pattern or field, you could look at the radiation pattern of an antenna using a field strength meter. And another use for the field strength meter is close-in direction finding. So if you thought there was interference or another signal close by, you could use a field strength meter to really find out where that source is. So they can be handy that way. All right, let's see now. Questions, HF antennas. What is the approximate length for a half-wave dipole antenna cut for 14.25?
Delta.
Very good. Yep. All right, what is the approximate length of a half-wave dipole antenna cut in the 80 meter range, 3.55 megahertz?
C.
Yeah, C, Charlie.
Yep, very good. All right, which of the following is an advantage of a horizontally polarized as compared to a vertically polarized HF antenna?
Alpha.
Alpha.
All right, very good. Lower ground reflection losses. What is the near vertical incidence skywave, also known as NVIS propagation?
I think that's B, Bravo.
Yep.
Yeah.
Yeah, short distance for medium or high frequency propagation. All right, which of the following antenna types would be most effective as a near vertical incident NVIS antenna for short skip communications on 40 meters during the day?
I'm saying A because I remember 1/10.
Yeah.
All right, very good. And a quarter wavelength above the ground.
Right.
How does the feed point impedance of a half wave dipole antenna change as the antenna is lowered?
E is in Bravo.
All right, very good.
Yep.
All right, how does the feed point impedance of a half wave dipole change as the feed point is moved from center to the ends?
My guess is Charlie, but I'm not sure.
Now here they're really looking for a magnitude. Does it increase or decrease?
I say A alpha.
A. Yep.
Yep, it increases. If you remember, it was the center fed dipole was much lower impedance. What is the most common name of a dipole with a single central support?
An upside down V,
Yeah,
meaning
A.
A.
Yeah, inverted V. What is the feed point impedance of a end-fed half wave?
D.
All right, very good. And not that that's bad. There are transformers, matching devices we can use to correct that. All right, what is the radiation pattern of a dipole antenna in free? Let me start again. What is the radiation pattern of a dipole antenna is free space in a plane containing the conductor? So this is a dipole free space.
So dipoles omnidirectional, right?
No, well, no. What are they talking about here? No, dipole has lobes to it.
I'll say D delta.
You know, you are close. It's a toss up between A and D. The figure eight comes in. If you remember, the dipole had strong radiation patterns opposite of each other, but the figure eight created kind of those zones where you didn't hear much or couldn't transmit because it was the figure eight pattern.
Oh, okay.
All right, in what direction is the maximum radiation from a portable VHF, UHF halo antenna?
I thought that was Charlie.
Yeah.
Yep, omnidirectional in the plane of the halo. How does antenna height affect the horizontal, the azimuthal radiation pattern of a horizontal dipole HF antenna? So antenna height here can be adjusted so you do change the pattern, radiation pattern. So that eliminates B. And we really haven't talked about anything becoming unpredictable with antenna patterns. So it leaves us with, if the antenna is less than a half wavelength high, that horizontal pattern is almost omnidirectional.
You beat me to it.
All right, which of the following best describes the radiation pattern of a quarter wave ground plane vertical antenna? And this is one of the good features of vertical antennas just in general, even mobile.
I'd say D delta.
Yeah.
Yep, very good. All right. What is the approximate length of, or for a quarter wave vertical antenna cut to 28.5?
C, 16 feet.
Well, you've got the half wave there. So the quarter wave would be half of that. So that would be the half wave length. And that, remember, that was the one that came up to 8.2, but they rounded to
8.
8, yeah. All right, where should the radial wires of a ground mounted vertical antenna system be placed? Radial system.
C.
Charlie.
Yeah.
Yep. Yeah. The key there is on the surface or just a few inches below. You don't gain anything by going deeper. All right. Which HF antenna would be the best to use for minimizing interference?
Charlie.
Yep.
Yep. You just turn it in the away from the direction of the interference. How do the lengths of a 3-element Yagi reflector and director compare to that of the driven elements?
Alpha.
Oh, alpha, yes.
Yes.
Yep.
All right, what is the approximate length of the driven element of a Yagi? Of course, we never had talked about anything being 3/4 or 1 wavelength.
Half wavelength, B.
Very good. All right, how does increasing boom length and adding directors affect a Yagi antenna?
A, alpha, gain increases.
Yep.
Yeah.
Yep.
Increase the power you're radiating in that direction. What is meant by the term main lobe of a driven, of a directive antenna?
Delta.
Yeah.
Yep.
Yep, that's the direction of the maximum radiated field. All right, what does front to back ratio mean when you're talking about a Yagi antenna? And here,
Charlie.
front, yeah, front to
Yeah.
back is, the power in one direction compared to the power in exactly the opposite direction. Which of the following can be adjusted to optimize forward gain, front to back ratio, or SWR and bandwidth of a Yagi antenna?
Delta.
Yep.
All of those are correct. All right, which of the following would increase the bandwidth of a Yagi?
Alpha.
I think alpha.
Yeah, it's the diameter
Yep.
of the element. It's which of the following is an advantage of using a gamma match when used with a Yagi antenna? And this was kind of a construction advantage.
I'm thinking alpha.
Oh, yeah.
Yep.
All right. What is a beta or hairpin match?
Alpha.
Alpha.
It's that stub placed at the feed point, help adjust. All right, what is the advantage of vertical stacking of horizontally polarized Yagi antennas?
Delta.
Yeah, remember in that one photo, it showed one horizontal polarization and then the other example vertical, but both, it narrows the main lobe in that elevation. Right, how does the gain of 2 3-element horizontally polarized Yagi antennas spaced vertically 1/2 wavelength, 1/2 wave apart from each other, typically compared to the gain of a 3-element?
Bravo.
When in doubt, go 3 decibels.
Yep.
That's
Yeah.
it's not a bad thought, because that's very, as you already well know, that's a very common expression. What is the primary purpose of antenna traps?
Alpha.
Yes.
Yep.
So that allows you to operate on multiple frequencies with one antenna, not having to put up multiple antennas for different frequencies. All right, which of the following is a disadvantage of multi-band antennas?
Delta.
Yeah,
Yep.
they have poor harmonic rejection. And those traps also have losses, so they can be a disadvantage.
No free riding antennas, right?
You're right. Yep, that's exactly it. Laws of physics won't let you buy with anything. All right, what is one disadvantage of a directly fed random wire antenna? A disadvantage.
Ooh, bravo.
Yep. Bravo.
Yep.
Those unknown burns.
Yep. What type of device is used to match transmitter output impedance to the impedance of a not equal to 50 ohms, something of not 50 ohms?
Charlie, you were
Yep.
talking about how you like
Charlie.
antenna tuners.
Yeah, exactly. What is meant by the term dBi and dBd when referring to antenna gain?
All right. So where's the answer that has misleading information that we're trying to do? Mislead people buying the antenna?
I'll tell you what, to the key. Oh yeah, that's here. Well, what you might remember here is dBi is for the isotropic. So the I
So
is used because it's an isotropic, kind of this mythological standard. So
alpha, right?
yeah, so
Yeah.
alpha and dBd, D as in dipole.
Dipole. Yeah.
And here's your answer you just said. How does the gain stated in dBi compare to the gain stated in dBd for the same antenna?
B. Bravo.
Bravo.
Yep.
And they tricked me on that, although I do like the antenna, so I'm not going to complain. All right, in which direction or directions does an electrically small loop, meaning less than a third wavelength in circumference, have nulls in its radiation pattern?
Bravo.
Yeah.
Yeah. Bravo.
And the broad side of the antenna itself. All right, what is the combined vertical and horizontal polarization pattern of a multi-wavelength horizontal loop antenna?
Charlie.
I would guess alpha, but it's a guess. See,
Well,
told you I was wrong.
Charlie was first.
Yep.
Virtually omnidirectional with a lower peak vertical radiation angle. All right, approximately how long is each side of a quad antenna driven element?
Alpha?
Yeah.
Yeah. A.
Yeah, because there are 4 sides, so quarter wavelength. How does the forward gain of a 2-element quad antenna compare to the forward gain of a 3-element Yagi?
Alpha.
Yeah, roughly the same.
Yep.
Mm-hmm.
All right, what configuration of the loops of a 2-element quad antenna must be used for the antenna to operate as a beam antenna, assuming one of the elements is used as a reflector?
I remember a ball and transformer being talked about here.
Yeah.
So alpha is my guess. Well, I'm not sure on that.
No, trying to see if there's anything to the memory jog.
I remember the reflector had to be bigger, but I don't know about shorter or longer.
Well,
Yeah,
bigger,
D.
bigger is
Yeah.
long.
D.
Yeah, so it has to be longer
Okay.
than the
So
drip.
bigger equals longer here. Sorry.
Yeah, for here. All right, which of the following describes a log periodic antenna? And the key to this is the question log, and then the answer, there's 2 that have that.
I think it's A.
Yeah,
Yeah. A.
yeah, the spacing varies logarithmically along the boom. Which of the following is an advantage of a long log periodic antenna. Remember, this was the antenna that's nice because you could receive a greater range of frequencies, even being directional.
I see A.
Yep.
Wider bandwidth. What is the primary use of a beverage antenna? And it really has one use. Beverage antenna is not a transmitting antenna, and it's certainly not portable. Some of these things get very, very long.
Well, that leaves A.
alpha.
Yep. A.
Yep.
I want
Good.
you around when we take the test.
All right. Which of the following most limits an HF mobile installation?
Charlie.
Charlie. Yep.
Yeah, Charlie.
Yep, the efficiency. What is one disadvantage of using a shortened mobile antenna as opposed to a full size antenna?
Alpha is a guess, but also Charlie, you talked about they're limited
Yeah.
because
Yep.
of the bandwidths that can
Yeah.
be used.
Yeah.
You have a much narrower bandwidth can be problematic because you can only get to a certain part of the band. All right, how does a screwdriver mobile antenna adjust its feed point impedance? And remember how they're made, the screwdriver antenna.
C, Charlie, by extending and retracting the whip.
Thought it was Bravo. I think he's thinking the same thing, but you could move that base load up and down.
Oh, yeah.
Yeah, so if you remember, that was an inductor. So there's a metal conductor. They're sliding up and down that wire coil, adjusting the inductance. You know, C is correct, but it's the kind of thing where C is correct, but B is more correct because it tells you what it's actually doing. You know, technically you're moving that section up along the inductor, but when you move it, the whip has to move too because it's attached to the top, but that's not the correct one. All right, what is the purpose of a capacitance hat on a mobile antenna? And this is, again, a good mobile example of kind of the restrictions we have or constrictions of being mobile.
Charlie is going to be my
Charlie.
guess.
Yep.
Yeah, Charlie.
Electrically lengthens something that's already short because of being mobile. All right, what is the purpose of a corona ball on an HF antenna?
Delta. That's what I thought you were
Delta.
asking the previous question. So kept looking for that answer.
Oh, yeah. All right. Let's see. Which of the following must be connected to an antenna analyzer when it is being used for SWR measurements?
Charlie.
I say,
Yeah, Charlie.
Oh. Yep.
okay, we don't have to have the transceiver on there at all?
You do not want the transmitter on. The antenna analyzer only takes microvolts. If somebody were to connect, and this has happened,
Mm-hmm.
an antenna, a transmitter up to that they blow it in the first second.
Ouch.
Even static electricity that's present on a long wire antenna can blow the meter. So you have to short that out first. All right, what is a use for an antenna analyzer other than measuring the SWR of an antenna system?
C,
Charlie, you said, right?
Yep. C.
Checking
Yep.
that unknown cable.
Very good. What problem can occur when making measurements on an antenna system with an antenna analyzer?
Bravo.
Yep. Any
Yep.
stray signal, strong signals can wreak havoc on the measurement. Which of the following instruments may be used to monitor relative RF output when making antenna and transmitter adjustments?
Bravo?
I'll say alpha.
I like alpha
I
because
think A. Yeah.
yeah, you're measuring the field strength
Oh,
from a antenna.
I misread the question. I was looking for something you could actually change, not just read.
Oh, yeah. All right, which of the following can be determined with a field strength meter?
Bravo.
Yep,
Yeah.
you could do that, the radiation pattern. All right, so that is what number? I think we have 2 more to go, so let me look here. Do you want to break or keep going?
We're taking a couple minute break here.
Yeah, it's
Sure.
just a quick 2 or 3 minute bio break.
How about 5 minutes to about 4:30?
All right, sounds good.
All right, sounds good.
Perfect.
Okay. All right, everyone, get up. Go take a break, get something to drink. We will resume here in about 4 to 5 minutes at the bottom of the hour, 4:30 in the afternoon in 4:30 in the afternoon in Texas Central Daylight Time. So got about 25 watching now. So thanks for sticking with us, guys. We were done by this time last week, but today's sessions are going a little bit longer. That's okay. It's all good information. And again, these will be replayable on the channel after the videos process on the back end on YouTube. And then you can go back and rewatch them as many times as you want to, like a regular YouTube video after the live stream ends. So be sure to check out the stream tomorrow. Be doing my regular first and third Sunday live stream that I've been doing since January of 2020. Be doing that tomorrow at 7 p.m. Central Time, 7 p.m. Texas time. We'll be talking to Christian, K0STH from 100 Watts and Wire. He's recently started streaming YouTube episodes, as well as doing his audio podcast, 100 Watts and Wire. So he's been on a couple episodes of the YouTubers Bunch a few months back, actually. And I guess during the whole COVID pandemic thing, he decided to start doing some YouTube stuff. So we're going to talk to him about that, get his backstory on that, get his schedule of when he'll be on. Let me turn that up real quick. When he'll be on, when you can catch him, what his YouTube channel URL is. You can go search for him now. You can go to YouTube and just search for 100 Watts and Wire and find his channel out there right now. And I think he does some cross posting between his audio podcast and his YouTube channel. I'm not 100% certain on that. Again, come join the stream tomorrow. Get to talk to him. Should be a good show. Additionally, the big part about tomorrow's live stream is that I'm going to be announcing a pretty big giveaway. Pretty big giveaway. In celebration of 50,000 subscribers on YouTube, we're going to be giving away a pretty big item. And then some smaller items. Got a donation of a tornado alert station from tornadoalert.com. Those guys were kind to donate that. We got a donation from RNL Electronics of a couple of Nano VNA devices. And I've got some other swag packs from ICOM to give away. So I wonder if you can guess what the big prize is now. This should be fun, man. I've been looking forward to this for a while. So looking forward to doing a really big giveaway. We will announce the giveaway tomorrow, and I'll share a sign-up form with everybody, which I created yesterday. It's up there now, but I haven't shared it. Nobody's signed up yet because I haven't shared it anywhere. But after tomorrow night, I will be sharing the heck out of it. And then we'll do a drawing, an announcement, a live drawing, a live giveaway on the channel 2 weeks from tomorrow on Sunday, October 18th. I think that's the right date, whatever 2 weeks from tomorrow is. Yeah, that's right. Yeah, 4 plus 14 is 18. So anyway, all right, they're just about ready here.
Yeah, the next chapter here is coax cable. Well, I've got 4:30, so I guess we should begin. All right, so 2 more to go, coax cable, and then 18. I think 18 is fairly short. All right, so coax cable has a term that we call characteristic impedance. And the 2 most common characteristic impedances we find in amateur radio are first 50 ohm and then second 75 ohm. So 50 and 75 ohm are the typical characteristic impedance of coax cable used for antenna transmission lines or feed lines. And I guess from those 2, 50 ohm is the most common.
Isn't 75 ohm used for cable TV?
I think cable TV may use 75. Of course, the issue with that cable is not so much the 75 ohms. We could work with that. It wouldn't be
The
able
shielding.
to transmit power
Ooh.
because cable TV isn't transmitting power to our TV. Well, I mean, it is very small signals, but so here's what typical coax looks like on the left. That's kind of a goofy drawing, but the plastic outer jacket is generally black. There's an inner shield. The shields are more common here on the right, what you will see listed here.
Quick question.
Sure.
So when you get this kind of cabling, you're going to want to buy something that's specifically made for ham radio.
Exactly. But if you go to places like DX Engineering, Ham Radio Outlet, that's pretty much all they sell is cable for the ham world.
Gotcha.
But I would say this is an area where too many hams try and cut corners. They look for the lowest cost cable because they may be buying, 50 feet, 100 feet, or 300 feet. So they try and save a little money. This is probably an area you don't want to skimp on because I'm not going to mention any countries, but there are manufacturers that make very poor quality cable and stamp it as if it's made to some particular standards. So you want to stick to major manufacturers, and that's generally what you'll find, say, at DX Engineering, Times Microwave, for example. So now here's a characteristic of cable. The attenuation of a coax cable increases. So the loss in signal of that in that coax cable increases as the frequency of the signal it's carrying increases. And if you think about it, take this picture, you've got a conductor here, this brown area, and you've got this brown area here, which is a conductor, and you've got this dielectric insulator. Well, if you think about it, that's the definition of a capacitor, 2 conductors separated by an insulator. So the higher the higher you go in frequency, the higher the losses would be, which means you have to be careful when you buy coax. Are you buying it for the VHF, UHF region, or are you buying it for, HF? There are cables that are made specifically for HF and then specifically for VHF, UHF. And when you look at cable, the losses are expressed in decibels per 100 feet. So the manufacturer may say, well, our coax has a 1.2 dB loss, and that means 1.2 dB loss per 100 feet. So if you're going to get 200 feet, it'd be 2.4 dB. And you will have to memorize this chart for the test. Just kidding. So this is a common coax chart And what it shows you is the use is here on the left. What frequencies are you going to be using? Are you going to be transmitting down this cable? And then it says, well, for HF, here's the loss, remember, per 100 feet. HF, VHF, and so on. So you got different cable types here across the top. And then they give you the losses at different frequencies. So if you were interested in just setting up your VHF antenna, you would go to somewhere between 100 and 200 megahertz. You know, VHF is, say, 146 megahertz. So you would look for a cable that has low loss, something like RG11, RG6 has lower loss. If you were in the HF range, say 10 megahertz, RG213 has less than a dB per 100 foot loss. So these tables are all over the internet. And on the very bottom here, they show impedance, the characteristic impedance. And of course, RG6, you've then stepped up to the 75 ohm range. All right, the percentage of power loss that would result from a transmission line loss of 1 dB would be approximately 20.5%. So you keep that in mind when you think about that loss table we just looked at. And the distance between the distance between the centers of the conductors and the radius of the conductor determines the characteristic impedance of a parallel conductor antenna feed line. So it's the difference between the center conductor and the radius of the conductors themselves. How large the cable is determine the characteristic impedance. So they'll build it, to be 50 ohms, in our case, 50 ohms or 75 ohms. Now, other services use different, like here, 450 ohms is a characteristic impedance of a window line parallel transmission line. Here are some examples of that. A lot of folks in amateur radio use this 450 ohm window line. It's far less expensive than coax. And it can be easier to work with in some applications. Here's an older example of a parallel two-wire system. And then this you don't see much in the regular ham radio world, but the air dielectric. And this little clear thing here is just a spacer to keep that center tube from hitting the shield right there. So there are some pretty extravagant transmission lines out there. All right, to prevent standing waves, SWR, on an antenna feed line, the antenna feed point impedance must be matched to the characteristic impedance of the feed line. So most all ham radios have 50 ohm termination impedance at the back of the radio. So you want to make sure you have a 50 ohm transmission line to connect to it. If there are issues, say, with the antenna not being exactly 50 ohms, then we can use an antenna tuner to help match those two together. And I think you've probably come across the term standing wave ratio, but standing wave ratio, or SWR, can also be determined with a directional watt meter. Here is probably the most famous meter for decades. It was called the Bird meter. So you'd have your transmitter coming into this meter on the left. The antenna would connect on the right side here, go out to the antenna. And then there'd be a slug right here in the center that would be in the frequency band you're going to use it on. And this meter was made for decades and decades up in Cleveland, Ohio. And then Bird, B-I-R-D, sold out, can't think of the name of the company, but they could measure power going from the transmitter to the antenna. You twist this slug right here. You can't really see that, but you can turn it, And then it measures the amount of energy coming back when you're transmitting. That gives you your standing wave ratio, the VSWR, or the standing wave ratio. In the bird meter here's on the right. These go for pretty high price use, but the Bird 43 was the classical one, but they don't really make that one anymore. But you've got Daiwa, Kenwood, MFJ makes, all of those companies have them. And these meters, well, the one on top, the Daiwa, one needle goes up to show you how much transmitted power. The other meter, other needle goes up depending on how much return energy there is. And where those two cross give you the SWR. So very practical and very important, something you don't want to skimp on in your station. All right, a difference between feed line impedance and antenna feed point impedance is a reason we have reflected power at the point where a feed line connects to the antenna. So the reason we have reflected power is the antenna is not perfectly matched to the radio. So you get what we call a reflection. So the original signal is in blue. The reflection, meaning the signal that's coming back, not absorbed or transmitted by the antenna, comes back to the transmitter this way and creates a standing wave right here. Those two add together algebraically. So this detracts from your transmitted power, but it also, if this reflected power is too high, you can really do damage to your radio if SWR values are too high. And here's the equation for calculating the voltage wave standing ratio. Ferrite bead or core reduces common mode RF current on the shield of a coax cable by putting an impedance in the current path. So ferrite beads, remember those from earlier, or cores, can reduce common mode RF current, meaning this reflected wave, by creating high impedance in the path of the reflected wave. So here's an example. Here's your shielded cable. Here are some common mode coils that are put in place. Here's example on the left side. So those can be used to block that common mode RF current. Now, what we're after is perfection, which would be a standing wave ratio of 1:1, meaning all the energy leaving the transmitter is going to the antenna and being radiated out. And that will result from a 50 ohm feed line with no reactance, where X of C equals X of L, and the load is a pure 50 ohm resistance. Now that's in theory. We can get very close to 1:1. I know my setup here, I have a little trouble getting to that perfect score, but I get with an antenna tuner, I can get pretty close to that value. So standing wave is impedance going forward versus coming back. In this case, it's 50 ohms both ways, so you get a 1:1 standing wave. So if you hear somebody say, oh, they've got an SWR of 1:1, they've got their system set up and tuned. And if you remember, I think earlier in our section, and maybe even other general sections you've taken, the whole idea in this is to get maximum power transfer. When your impedance of the radio matches the antenna or the load, you get maximum transfer of power, energy, out. And that's what this all boils down to.
Quick question.
Yes.
Is there some sort of rule of thumb for a minimum acceptable
That's a great
SWR?
There's a very good question. So most radios sold today have internal antenna tuners built into them. So the ones I showed you earlier, you don't have to buy those if your radio has one built in. Those generally will tune up to about a 10-to-1 mismatch, and will be able to take it down to 1-to-1 or very close to 1-to-1. The rule of thumb, though, is you want to try, when you're putting an antenna up, you want to try and get that as close to 50 ohms as you can. That's difficult because a lot of different things influence the impedance. So the rule of thumb is generally if you can get a 3-to-1 ratio on your antenna, you're okay. Most modern radios will handle that. And certainly with the tuner, it will tune up just fine. Anything greater than that, though, you've got to really go back and adjust the antenna length, the height, the feed point, something's off. And it can be experimental like that. There's nothing, there's no playbook like the Cowboys to say, if your SWR is 10-to-1, look here. I mean, there are a number of things that influence that. So.
All right, thanks.
All right, coax cable, there is an interaction between high SWR, which is bad, and transmission line loss, in that if the transmission line is lossy, having high SWR will increase the loss. So you've got high loss in your transmission line because it's lossy. It's got water in it. It's not good quality coax or whatever. But if you have transmission line losses, it's going to make whatever your standing wave ratio is even larger. And if SWR is measured at the input to the line with higher transmission line loss, the more SWR will read artificially low. So there are two things here. You generally want to measure the SWR of an antenna as close to the antenna as you can without influencing it by you being too close. But you also want to measure the SWR right down to on the cable where it connects to your radio to make sure there are no problems with the coax. You could have impedance problems due to the antenna, and you can have impedance problems like they mentioned here, a lossy transmission line. So if SWR is measured at the input to the line with higher transmission line loss, the more SWR will appear to be artificially low because you've got losses in the line and it's not getting as much signal as it needs. What I do with my coax is I'll take a length of the coax that I'm going to use. I put a 50 ohm load at the end. I put the analyzer on the other end and make sure that the coax is 50 ohms with no X of L or X of C. And SWR will always be lower at the input end of the lossy transmission line. But again, you can measure that with a antenna analyzer. And like I mentioned, you should try, if possible, to measure the SWR right at the antenna, because that tells you the characteristics of the antenna. And if the antenna transmission line is lossy, the reflected power will be attenuated, which is not a good thing, just as it will attenuate the forward power. So lossy transmission line makes bad SWR look better, but it's artificially viewing it that way. And for this type of antenna, a common way to adjust the feed point impedance of a quarter wave ground plane antenna. This, by the way, is a very common antenna for VHF, UHF, and then to some extent for HF. But a way to adjust the feed point impedance so you can get to 50 ohms is to slope these four radials. You might think they normally came out horizontal, but to adjust the impedance, you bring these down and it changes the characteristic impedance. All right, connecting a 50 ohm feed line to a non-resonant, I'm sorry, let me back up, to a non-reactive load having 200 ohm impedance will result in an SWR of 4:1. So you've got 200 over 50, 4:1. That's not a good match at all. You want to correct that. Connecting a 50 ohm feed line to a non-reactive, X of L equals X of C, so it's not reactive. Having a load of 10 ohm impedance results in a 5:1 SWR mismatch. And here are those meters. The one on the left is best. So here we can see, I'm going to assume, let's say they're on a 300 watt scale. So they're transmitting about 200 watts. They are reflecting where these cross is the SWR. So this is 1.7. This is about 2:1 here from what I can tell. And over here, the standing wave ratio is very high. You can tell where these needles cross, it's off the scale. So this would be very bad. You have very little forward power on this scale and a whole lot of reflected power. So that's where these meters come in handy. And I always check my SWR at about 25 watts. So if I do have high reflected power, I don't destroy anything in the process. All right, the SWR on an antenna feed line is 5:1. The matching network at the transmitter end of the feed line is adjusted to a 1:1 SWR. The resulting SWR on the feed line is still 5:1. So SWR is determined by the load impedance because it's looking at the comparison of the load impedance to the transmitter impedance. Now, I'm not sure why this is in here, but this is what we call an N connector. These are very popular outside of the US. We tend to use the PL259. You'll actually buy radios and they'll have these N connectors on them. But a lot of people swear by them. They're supposedly low loss. An N connector is a moisture resistance RF connector, useful to 10 gigahertz, which is better than the more common 259.
Is that the Motorola connector?
No, there's an NMO, which is the new Motorola antenna connector, but that's the base the antenna screws into.
Oh, okay.
That I'm familiar with. So other connectors, maybe you have a handy talkie, and HT might have, the older ones had a BNC. The newer ones have these SMA connectors. Here's the 259, which in the US is very popular, not as complicated as this N connector. And then the old F connector, which we see with cable TV. And by the way, you have to be careful of these. Again, I'm not going to point or single out countries, but there are countries that make these by the shipload, very poor quality. And again, these are not areas you want to cut costs on. The SMA connector is a very small threaded connector suitable for frequencies up to many gigahertz. So it's very popular. Here's a barrel connector for an SMA. This is a jumper here. This is a female connector. I guess that's the male, and here's a male example. So the SMA is very popular. The Chinese and Japanese certainly like them on their handy talkies. We commonly use the PL, meaning plug, PL259 connector, or RF connections at frequencies up to 150 megahertz, which covers your VHF band, but not your UHF band. And this is what, this is a barrel connector to connect two of these together. Say you had two coax cables you needed to put together, you screw these in. And these solder in. You can get these as solder type or crimp actually. And there's a jumper with a PL259 and an SO235 connection. This would plug into that, but it's used for a jumper to go somewhere else. Okay. What are the typical characteristic impedances of coax cables used for antenna feed lines for amateur radio?
Bravo.
Bravo.
Very good. How does the attenuation of coax cable change as the frequency of the signal it is carrying increases?
Charlie.
Yep,
Yeah, remember.
Charlie.
Oh, no.
No, Bravo. The
Yeah.
Bravo.
attenuation
Oh, yeah,
or the
Bravo.
loss increases.
Yeah, remember attenuation is a loss. We attenuate, make smaller. All right, in what units are RF feed line losses usually expressed? So if I said the coax feed line you're using has a 1.2 dB loss, what do I really mean?
D.
Delta
Delta.
Per
per
100?
100 feet.
Yeah.
You helped us narrow it down to decibels.
Pardon?
You said decibels. Only two of the answers had decibels in them. The other two had ohms.
Oh, I didn't even notice that. Okay, what percentage of, I did get that right?
Yeah.
Yeah.
Oh, I see what you mean. Yeah, that's trick. Okay, what percentage of power loss would result from a transmission line loss of 1 dB?
C.
Charlie.
Charlie.
Yep, 20, and that's quite a bit. 20 point, oops. Well, I did something here. 20.6, which is a fifth of your power. All right, which of the following factors determine the characteristic impedance of a parallel conductor antenna feed line? This was two basic measurements.
Alpha.
Yeah.
Yep.
Alpha, the distance between the centers of the conductors and the radius. What is the typical characteristic impedance of window line, which some hams like, older hams, parallel transmission line?
Delta.
D. Delta.
Yep. What must be done to prevent standing waves on an antenna feed line?
D's only one that makes sense to me.
Yeah.
Yeah. Delta.
Yeah, that's it. You want to match those impedances. Not only does it give you the best SWR, it also allows you to transmit maximum power. Which of the following can be determined with a directional wattmeter? Remember those?
Alpha.
A. Alpha. Standing.
Yeah, if you remember the meters we just looked at, those meters can measure forward and reverse, and where those needles cross is our standing wave ratio. What is the reason for the occurrence of reflected power at the feed point where a feed line connects to an antenna?
Charlie, I think.
Yep, difference
Yeah.
in impedance, feed point impedances. How does a ferrite bead or core reduce common mode RF current on the shield of a coax cable?
A.
Yep. Alpha.
Creating an impedance in the current paths. What standing wave ratio will result from the connection of a 50 ohm feed line to a non-reactive load having 50 ohm?
B.
Yeah. B. 1-to-1.
And that's exactly what you want. Yeah.
Nirvana.
Yeah, those two matching. And of course, part of the problem is too, our feed line or antenna isn't purely non-reactive. It has some reactance or capacitance in it.
That's what had me pause. I was looking at non-reactive. That wasn't mentioned when we talked about it in the class, was it? I don't
Yeah,
remember.
I think so, and I thought I mentioned non-reactive means X of L equals X of C, so the two
Gotcha.
cancel out.
Gotcha. Thank you.
And if they're not equal, they don't cancel out. So you might have some reactance or some capacitance. All right, what is the interaction between high standing wave ratio, SWR, and transmission line loss?
I think Bravo.
Yep, you're right.
Yep.
If a transmission line is lossy for whatever reason, there are many, high SWR will increase the loss. What is the effect of transmission line loss on SWR measured at the input to the line?
Bravo, I think.
Yeah.
And if it wasn't
Oh.
Bravo,
Oh, it's alpha because
Hey.
it'll be artificially low because it'll get higher
Oh,
at the
yeah.
antenna. That's right. It's alpha.
it makes it look artificially low, which kind of tricks you, you don't realize it. All right, which of the following is a common way to adjust the feed point impedance of a quarter wave ground plane vertical antenna to be approximately 50 ohms? So remember that diagram that had four
Mm-hmm.
B, Bravo.
Bravo. Slope them down.
Exactly. What is the standing wave ratio, or what standing wave ratio will result from the connection of a 50 ohm feed line to a non-reactive load having 200?
A, 4-to-1.
4-to-1.
Exactly. Not really a good one. What standing wave ratio will result from the connection of a 50 ohm feed line to a non-reactive load having 10 ohms?
B, Bravo, 50-to-1.
5-to-1, I guess.
Yeah, yeah.
That's
Duh.
I know what you meant.
Yeah, we knew that. Yeah, it's 50 ohm and 10 ohms, so 5-to-1. All right, if the SWR on an antenna feed line is 5-to-1 and a matching network at the transmitter end of the feed line is adjusted to a 1-to-1, pardon me, SWR, what is the resulting SWR on the feed line?
B,
When
5-to-1.
or 1-to-1.
5.
Ah,
Yeah, B.
B. Yeah, I'm changing my answer.
And the reason is the SWR is really determined by the load. All right, now we jump connectors here. Which of the following describes a type N?
A, Alpha.
Moisture resistant.
And good to 10 gigahertz. And there are parts of the hobby that go way up there in frequency, microwave stuff. All right, what is a type of SMA connector? Which are very,
B, Bravo.
Yep.
yep. And
Yep.
what they're for is they're also good up to several gigahertz. Which of these connector types is commonly used for RF service at frequencies up to 150? Very common in the US.
PL 259. C, Charlie.
Charlie. RJ11's funny. Phone connector.
That's right.
Right.
All right. So we've got one more. And before let me see, we've got 18. So do you want to take a break or go through?
I'm
I
done.
say you go through it.
I'm okay.
Yeah.
All right, let's do it then. So let me make sure I'm on 18, right? RF safety. All right. You guys, by the way, have been great. I appreciate it. All right. So back to that old list, which is getting very small now. RF. Okay. So RF electricals and electrical safety. Turn off the transmitter and disconnect the feed line whenever you make adjustments on or repairs to an antenna. I have a friend in Tennessee who has a cell site business, and they are just super careful that they shut off all the transmitters of everything on the tower before they'll even climb. And any person preparing to climb a tower that supports electrically powered devices really must make sure all circuits that supply that power are locked out and tagged knowing that they're off. And one of the practices that should be observed for safety when climbing on a tower using a safety belt or harness is always attach the belt safety hook to the belt D-ring with a hook opening away from the tower. You don't want any possibility of that hook opening. And just on a side note, just too often in amateur radio, we read about folks who climb a tower and have issues because they're not doing it safely. So if you ever get into that situation, make sure you look to safety. This guy even has some fall restraints here. So if he were to fall, these yellow cords are shock absorbers and they'd stop him. It wouldn't be pleasant, but it would break his fall. So always disconnect the feed line from the transmitter before going up on a tower to work. Prevents accidental RF radiation and also getting shocked and then causing trouble with you holding on. Okay, an amateur operator must perform a routine RF exposure evaluation to ensure compliance with RF safety regulations when transmitter power exceeds levels specified in the FCC Part 97.13. And I don't remember what those are. If you install an indoor transmitting antenna, make sure the MPE limits are not exceeded in occupied areas. I hear of hams all the time mounting antennas inside their shack. And you always hope that it's low power because you're in that field of radiation. So that's kind of risky. And the MPE is the maximum permissible exposure. One way that RF energy can affect human body tissue is that it heats body tissue. And there are a lot of studies on that. I remember decades ago, I worked at TI, and we used to take our sandwich, our lunch, go up to the roof and put it in front of one of the feed points. This was back in the 70s before microwave. You put it there and it would heat up the sandwich, but it would also heat up your hand. So here's an example of a horn transmitter of some type in a testing room. And you never want to step in front of that for the reasons we mentioned earlier. Maximum power, high frequency is coming out of this. So you'll do cell damage with getting in front of that. And on transmit, it radiates a highly concentrated beam of RF energy, just like your microwave, but you're not in your microwave. You can determine that your station complies with FCC RF exposure regulations by calculations based on that bulletin, which I've never looked at, by calculations based on computer modeling. That's probably more accurate and quicker. And by using the field strength meter in calibrated equipment. All of those are possible. So the bulletin, computer modeling, and also the field strength meter we talked about earlier. And time averaging in reference to RF exposure means that the total RF exposure is averaged over a period of time. So it's not that one pulse. It wants to know how much energy and over what time. And here are some examples of much lower power, but exposure for a much longer period of time. On the far right, we have 1 minute, but very high exposure of MPE. So we want to be careful of that. And a general equation for time averaging is the exposure time is equal to the limit versus the time average. I don't think there's a question on calculating one of those examples. When evaluating RF exposure, a lower transmitter duty cycle permits greater short-term exposure levels. So what they mean here is a low duty cycle, meaning the transmitter is on for a very short period of time. So if that's true, you can handle larger exposures because the average time length is lower. And the following properties are important in estimating whether an RF signal exceeds the maximum permissible exposure, the MPE. The duty cycle, how long is it on? Its frequency, how often does it occur? Its power density, and all of those. So the duty cycle, the frequency, the higher, the riskier, and of course, the power density. And here are some examples of controlled versus uncontrolled power exposures. If an evaluation of your station shows RF energy radiated from your station exceeds permissible limits, you must take action to prevent human exposure to those fields. Whether it's you or your neighbor, you definitely want to take action. And using a calibrated field strength meter with a calibrated antenna can be used to accurately measure that. And here's an example of one such device. And a couple of others. One on the left looks pretty old. And the ones on the bottom are out of a Utah amateur radio group that are homemade. So that's interesting. All right, when installing a ground-mounted antenna, it should be installed so no one can be exposed to RF radiation in excess of the maximum permissible limits. So here, I guess this fella has this antenna in that wooden surrounding. I thought that was in his entire backyard, but apparently it's meant to keep people, because this is a highly directional antenna as well. So if you were to get your head up toward that feed point, it would not be good. If an evaluation shows that a neighbor might receive more than the allowable limit of RF exposure from the main lobe of a directional antenna, take precautions to ensure that the antenna cannot be pointed in their direction. Generally, this isn't a problem because your directional antenna is well above on a neighbor, or on a tower or on a roof. All right, electrical safety inside the ham shack is covered by the National Electrical Code. And you can probably find that on Amazon somewhere. RF exposure limits to the human body are covered by ANSI, but not by NEC, the National Electrical Code. So electrical safety versus RF exposure, two different places. Current flowing from one or more of the hot wires directly to ground will cause a ground fault interrupt, GFCI, to disconnect the 120 or 240 volt line power. One of the good uses of the GFIC is for that protection. And there are examples of those before and after. Those are, available at Home Depot or those places. And the ground fault interrupt is used to measure or look for a difference in the amount of current going from and returning to the service. or through the ground loop itself. So I have never connected these. We have a little bit of an older house. I don't think we even have any anywhere in the house. So. All right. Now, bonding all equipment enclosures together helps minimize RF hotspots in a ham radio station. Generally, we talk about bonding with grounding, but here they separate them. RF bounding can be very effective even if a true ground is not available. Kind of gets back to that question, what if you're on the second or higher floor? Grounding ensures that hazardous voltage cannot appear on the chassis. Bonding and grounding are actually two different but related disciplines. And again, ARRL has a great book on grounding and bonding. Only the wires carrying voltage in a 4-conductor line cord should be attached to fuses or circuit breakers in a device operated from a 240 volt signal phase source. All right, 15 amps is the size of fuse or circuit breaker that would be appropriate to use with a circuit that uses the wire gauge number 14 wiring. And here's a wire table, which again is all over the internet, but let you know safety, I bought an amplifier for my station here. It's 500 watts, so I knew it would pull some current, but it could be wired to operate off of 240. So I converted a 120 line here because I knew if I ran it off of 240, the current draw would be much lower than if I was trying to do it off of the 120 side, because it's the same power, but you have twice the voltage. So, and people in homes have been noticed to seen to push this limit. Some people have been known to actually pull breakers out and put ones of higher value. Just be careful with the wire size and gauges and breakers.
That is very dangerous.
Oh yes,
Indeed.
And according to the code, AWG number 12 is the minimum wire size that may be used safely for a circuit that draws up to 20 amps. And yes, there are people that push that. Just ask any fireman, he'll know. And of course, thick or thin insulation can be misleading about the actual wire size. So you want to strip off some insulation and see what you really got. Right, the purpose of a transmitter power supply interlock is to ensure that dangerous voltages are removed if the cabinet is open. Some of these cabinets you open and you'll literally walk into. So they put these interlocks in to make sure they cut the power to the transmitter. You don't want to be inside a metal box and get electrocuted. One danger from lead tin solder is that the lead can contaminate food if hands are not washed carefully after handling. Same reason you use a special soap if you're at the gun range. And these are the symptoms. Good engineering practice for lightning protection grounds include bonding them together with all other grounds. We saw that earlier. Here's a really good example on the right-hand side. This person has a big panel. These are all pass-through connections here, but they're connected to ground. So any lightning attempting to come in is going to see that ground presence first. And then a little different ground connection system here on the right. Solder joints should not be used with wires that connect to the base of a tower to the system of ground rods, because the solder joint will likely be destroyed, very likely, if they take a hit with lightning. All right, danger of carbon monoxide poisoning is a primary reason for not placing gasoline-fueled generators inside an occupied area. You would think that's common knowledge, but not always. And when powering your house from an emergency generator, make sure you have a special switchover. You must disconnect the incoming utility feed power line. And for emergency generator installation, the generator should be located in a well-ventilated place. They've got one here showing in the back of a house. Gasoline-powered generators may emit exhaust gases that could be hazardous. And if you have a portable generator, now you'll see these generators a lot in field activities with ham folks, but they'll put the generator quite a ways away and then run an extension cord up to the radios. All right, now we've got our questions. What precaution should you take whenever you make adjustments or repairs to an antenna?
B.
B, but I like C.
Well, C wouldn't be a bad idea, but not in our application. Turn off the power. What should be done by any person preparing to climb a tower that supports electrically powered devices?
B.
B.
Yep, want to be locked out and tagged. Which of the following should be observed for safety when climbing on a tower using a safety belt or harness?
Delta.
Delta.
Yep, delta.
What?
Okay.
Now, if you thought A was correct,
B is more correct.
well, the belts today are designed so you can lean back on it. They'll support your weight. And you really don't want tools connected to the D-ring. The D-ring should just be for you and your harness. So you want to make sure the belt that is being used is rated for the weight of the climber. But you also have to remember, if a person falls from a tower and they don't have the bungee cord addition, the weight the weight that belt is going to experience, it is quite a bit higher than what they physically weigh. So, all right, which of the following steps must an amateur operator take to ensure compliance with RF safety regulations when transmitting power exceeds levels specified in Part 9713?
Delta.
Charlie.
C.
Yep.
Yeah.
I need to look that up. I don't think I've ever looked that
I don't
up.
think we've ever had, we don't have to post anything like that, do we?
No, that's a good point. Yeah, there were things many years ago we had to post, but that wasn't one. What precaution should you take if you install an indoor transmitting antenna? I would recommend never do it, but if you do.
C.
Charlie.
C. Yep, Charlie.
But that last one I said we had to post because I remember my dad had posters in his shack.
Yeah, I remember too, years ago. The only thing I remember now you're supposed to post is your license. But beyond that, I think the FCC is backed away from.
Okay.
All right, what is one way that RF energy can affect human body tissue?
A.
A.
Yep, heats up that tissue.
And sandwiches.
And sandwiches. How can you determine that your station complies with FCC RF exposure regulations?
Well, since I know B and C are correct, I'm going to go with D.
Yep, D.
Yep,
Yeah,
D.
remember when we were at that, we said those three things: the bulletin, modeling, and the field strength meter. All right, what does time averaging mean in reference to RF radiation exposure?
Delta.
D. Delta.
D.
All right, the total RF exposure averaged over some period of time. What effect does transmitter duty cycle have on evaluating RF exposure?
Alpha.
Yeah.
Yep.
All right, good. Lower transmitter duty cycle permits greater short-term exposure. What is the following? Which of the following properties is important in estimating whether an RF signal exceeds the maximum permissible exposure or the MPE?
Delta.
Yep.
Yep.
Yep, all of those. What must you do if an evaluation of your station shows RF energy radiated from your station exceeds permissible limits?
Alpha.
Yep.
Yep.
Alpha.
Alpha.
It's up to us to make sure we take action to prevent that. And what type of instrument can be used to accurately measure an RF field?
B. Bravo.
Bravo.
Yep. B.
And the key there is calibrated. You want to make sure it's you're getting a real number, or that the number you're getting is accurate. What precaution should be taken when installing a ground-mounted antenna?
D.
I'm guessing D because nothing else makes sense.
Yep.
That's a good way to discriminate between these. Yeah, you want to make sure nobody else that has no business being there can get access to it. What is one thing that can be done if evaluation shows that a neighbor might receive more than allowable limit of RF exposure from the main lobe of a directive antenna?
D. Delta.
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 Yep.
Yeah, we talked about that.
Yep, you want to make corrections to that. Again, it's up to us. A lot of the things in amateur radio, we have to, are self-policing. Which of the following is covered by the National Electrical Code?
Charlie.
Yep. Charlie.
All right, good. And which of the following conditions will cause a ground fault interrupt, GFCI, to disconnect the 120 or 240 volt AC line powered to a device?
Bravo, I think.
Yep.
Yep. And what technique helps to minimize RF hotspot in an amateur station?
Charlie.
Yep.
Yeah, back to that bonding, which is very closely related to grounding. All right, which wire or wires in a 4-conductor line cord should be attached to fuses or circuit breakers in a device operated from 240 volts AC single phase?
A. Alpha.
Yeah. A.
All right, only the two that carry voltage. What size of fuse or circuit breaker would be appropriate to use with a circuit that uses wire number 14?
D. Delta.
Delta. They make that easy.
Yeah.
100 amps.
Yeah. According to the National Electric Code, what is the minimum wire size that may be used for wiring a 20 amp circuit breaker?
Charlie.
Yep.
Charlie.
All right, Charlie, what is the purpose of a transmitter power supply interlock?
Charlie.
Seems like a lot of Charlie answers here, doesn't it? Which of the following is a danger from lead tin solder?
Alpha.
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 Which of the following is good practice for lightning protection grounds?
Delta.
Delta is my
Yeah,
choice.
Delta.
Yep. Make sure that everything is bonded together. Why should solder joints not be used with the wires that connect the base of a tower to a system of ground rods?
D,
Delta.
Delta.
Yeah. There goes my C idea. Which of the following is a primary reason for not placing gasoline-fueled generators inside an occupied area?
Alpha.
A, Alpha.
Yep, very dangerous. What must you do whenever powering your house from an emergency generator?
Alpha.
Alpha.
Yeah,
Get over here.
Alpha.
All right. Let's see. Well, I can't go any further. At the end?
We're at the end of the yellow brick road.
Yay.
Really?
So we've all passed. You can send us our. Oh man.
No, it just went forward. All right. Which of the following is true of an emergency generator installation?
Hey.
Yeah, A.
Yep.
Now we're at the end. All right. Well, my goodness, thank you. Thank you very much for being here. I know there's a lot of other things you could be doing, so
Thank you for your time.
Yes,
Thank you.
you're very welcome. If you ever have any questions or anything, just my email is my call sign, K5TGS at yahoo.com. So good luck with your test and good luck in the hobby. It's a great hobby to be in.
Thank you.
You're welcome.
Thank you.
Thank you very much.
You're welcome.
Thank you.
Figure out how to close this out.
All right, thanks a lot, Tim.
Thank you, Jason. Have you recorded this?
Yeah, it was live streamed the whole time.
Oh, wow.
Yeah.
Very
So
nice.
it'll be once I click on end here in a minute. The morning session was live streamed this morning, and I stopped for lunch, and that one should be replayable on YouTube already. But once I click end here, it'll take YouTube a little bit of time to process it since it's
Sure.
like 3 or 4 hours long. But after that, it'll be replayable on YouTube.
I'll look for it.
Okay.
Thanks very much. Have a good weekend.
Thank you. You too.
Bye.
Bye. All right, let's close that. And we're going to go here. All right, guys, that is it. That's the entire general course from the North Richland Hills Amateur Radio Club. 2 days, 4 sessions, 2 sessions per day, both today and last Saturday. They will be, once again, replayable on YouTube as soon as, as soon as YouTube finishes processing this last one. And a couple, 3 weeks from now, whenever I get time, well, I'm going to work on it, and they'll be available a couple, 3 weeks from now. I'm going to get time to go back, cut out the live stream intro, exits, the middle stuff, and all that, and cut them down into shorter sections. That's just the training. Just start with the training, go from there, cut them up into. I don't know if it'll be 4 new episodes or if I'll piece them together. I'm not sure yet. They're kind of long, so just be watching for it on the channel. Sign up for my email list, hamradio2.com/email-sign up. I will share them there when they are ready. I will share this playlist there and on Twitter and Facebook and everywhere where it's ready. Probably talk about it on the live stream tomorrow. Be sure to join the live stream tomorrow for the announcement of a huge giveaway for 50,000 subscribers on YouTube and for a chance to talk with Christian from 100 Watts and Wire 73. Everyone have a good Saturday evening. And hope to talk to all of you very soon.